Dear attendees, now it's the start of session 2, oil and gas, under the moderator, Dr. Abdul Shakur and Dr. Bilal Mansour. Dr. Abdul Shakur, the mic is yours.
Thank you very much, Ms. Noor, for the arranging this session. So it is my great pleasure to welcome all the respected presenters and all the participants to the second day of the second session, which is related to the materials for oil and gas. Just for the information of the general audience, this session is mutually organized with the support of Texas A&M University at Qatar and the Qatar University. So we have actually 10 speakers with us, and including the keynote speaker. So Dr. Michael is our keynote speaker, and he will be starting soon. Let me introduce Professor Michael as our keynote speaker. He's an associate professor in the material science and engineering at Texas A&M University, USA. He received his PhD in mechanical engineering from MIT in 2005, working with Elias Argon on an NSF fellowship. During 2005 to 2008, he was a director's postdoctoral fellow and technical staff member at Los Alamos National Laboratory. In 2007, Dr. Michael was honored with the LANL Postdoctoral Distinguished Performance Award. He received the TMS Early Career Faculty Fellow and NSF Career Awards in 2012, the MIT Graduate Materials Council Outstanding Teacher Award in 2014 and 2015, and the Texas A&M University 2000 Presidential Impact Fellow Award. In 2020, Dr. Michael established and directed a nationwide RE program, which provided fully remote summer research internship to 58 undergraduate students during the COVID-19 crisis and continues to operate the study. Currently, Dr. Michael serves as the director of the Center for Research Excellence on Dynamically Deformed Solids and NNSA Supported Center for Excellence. His group uses modeling and experiments to investigate solids under extreme environments. He is an author on over 120 peer-reviewed publications with more than 4,500 citations on Web of Science and H factor of 38. He is going to present on the mechanism of hydrogen-induced intergranular fracture in nickel basalite 725. Please welcome Dr. Michael, and session is to the Dr. Michael, please.
So thank you for that very kind introduction. Let me see if I can share my presentation here. Please tell me if it shows up. So do you see my PowerPoint presentation at this moment?
It's perfectly fine.
Okay, great. So I recall my visit to Qatar a few years ago very fondly, and I look forward to being able to visit in person again soon. In the meantime, I'm happy to be able to take some time to show you what we've been doing in the last few years. So the title of this talk is on the mechanisms of hydrogen-induced intergranular fracture in nickel-based alloy 725. It's a mouthful. I promised to unwrap all that during the talk. Before we move on, I wanted to specifically acknowledge the two students who really did all the work on this. The first one, Mengying Liu, recently graduated and moved on to a faculty position at Washington and Lee University, which is a top-ranked undergraduate teaching college in the US. And Lai Jiang also recently graduated and continues as a postdoc in my group. So the motivation behind what I'll be showing you today has to do with hydrogen embrittlement. So hydrogen embrittlement is a common concern in many oil and gas applications. If you were to expose a metal alloy to a hydrogen-rich environment, such as water, right? So basically any place on Earth is going to be hydrogen-rich. If you were to expose a metal to that kind of environment, it tends to take hydrogen, absorb hydrogen from the environment. And as it absorbs hydrogen, it becomes embrittled. And what we mean by that is that its ductility decreases, right? So its strain to failure decreases, its fracture toughness decreases, its fatigue life decreases. All of these things are concerns for technology. In face-centered cubic metals, such as nickel or nickel-based alloys, this embrittlement process is associated with a transition in the fracture mode from transgranular to intergranular. So here I'm showing you an image taken from a paper by Bechtel and others. On the left, you see nickel with no hydrogen. This is a fracture surface of pure nickel with no hydrogen. You can see lots and lots of dimples. That means that this sample fractured in a transgranular ductile manner. After introducing hydrogen, the fractured surface changes dramatically. It no longer has dimples. It has these very clean, flat facets, which are actually the grain faces left over from intragranular fractures. So there's this change in the fracture mode. Why does embrittlement occur at all? There are two competing theories. There are many competing theories, but there are two main theories, I think, that are typically cited. One of them is called hydrogen enhanced decohesion, or HEAD. And this theory, this hypothesis for hydrogen embrittlement is basically founded on the Rice-Thompson criterion of the brittle to ductile transition. Okay, so in this very simple idea, we suppose that there's a crack and there's some external load applied. And what the thing that determines whether or not this crack is going to propagate forward in a brittle manner, or whether it will become blunted and therefore, forced to propagate in a ductile manner, depends on the competition between bond breaking and dislocation emission from the crack tip. So let's suppose that we look at the region ahead of the crack tip. There's going to be a couple of, there's going to be atoms, pairs of atoms ahead of the crack tip. There are going to be bonds between those pairs of atoms. If you were to weaken those bonds, right? If those bonds were to become weaker, the material would become more brittle, right? So basically, the Rice-Thompson criterion says that as you increase the bond strength, the material becomes more ductile, right? Fractures in a ductile manner, versus if you reduce the bond strength, it becomes more brittle. The second factor that plays into this is dislocation emission, right? So in addition to breaking bonds ahead of the crack tip can also emit dislocations, okay? And the ease of dislocation emission, the ease of plasticity ahead of the crack tip has an opposite effect on the ductile to brittle transition. So basically, as the flow resistance increases, which means, for example, as the yield strength of the material increases, the material becomes more brittle, right? So in other words, increasing bond strength makes the material more ductile, increasing flow resistance makes it more brittle. So if you wanted to make something, let's say, more brittle, you would either decrease the bond strength or increase the flow resistance, or both. Now, in this picture, in the HEAD hypothesis, hydrogen embrittlement is thought to be due to the weakening of the bonds because in experiments, we see that hydrogen has very little effect on the overall flow resistance, like the yield strength in most materials. Certainly in nickel-based alloys, it has very little effect on the strength. So the embrittlement is thought to occur from the weakening of the bonds. The other hypothesis that is often proposed in connection with hydrogen embrittlement is known as hydrogen enhanced localized plasticity, or HELP. And in the HELP hypothesis, hydrogen is thought to promote fracture by enhancing localized plasticity. Now, if you have worked in the field of hydrogen embrittlement before, then you've probably heard of HELP many times, and so maybe you take it for granted. However, if you have not worked in this, or even if you have worked in this, it might be a good idea to think about what this means from the perspective of what I just told you in the Rice-Thompson criterion, right? So in the Rice-Thompson condition, increasing the flow resistance makes the material more brittle, reducing the flow resistance, right? So if plasticity becomes easier, the material becomes more ductile, right? That's the conventional view in the Rice-Thompson theory. In hydrogen-enhanced localized plasticity claims the opposite, right? It says flow becomes easier ahead of the crack, and that promotes fracture, right? So this is a very counterintuitive theory in many ways, and a very counterintuitive hypothesis. Now, to be fair, there are examples of situations where localized plasticity does lead to fracture and failure. And the sort of, I think probably the best known example is the case of shear bands in bulk metallic glasses. So, bulk metallic glasses are materials that are composed of metals, but they are not crystalline, they're amorphous, right? So here is a sample of a bulk metallic glass that was bent. And you can see that rather than sort of bending uniformly, it basically sort of fragmented into a stack of, sheets that sort of slid over each other. Okay, and these interfaces between these sheets are shear bands. Okay, and that's actually where fracture occurs. You can even see little cracks forming at some of these shear bands. So, intense localized shear does definitely lead to fracture in some cases. However, what is the evidence for hydrogen-enhanced localized plasticity in nickel-based alloys, in hydrogen-bearing nickel-based alloys? Well, it typically comes in the form of figures such as the one I'm showing you here on the right. This was taken from the group of Dirk Rabe at MPI at the Max Planck Institute in Germany. And they're looking at a fracture surface. And they see slip lines on the fracture surface. Is this evidence for help? Well, I would suggest that this is inconclusive, right? So because we don't know what the role of these slip lines was in the fracture process. Are they the cause or are they the effect? Did they promote the fracture or did they impede the fracture? We can't really tell just by looking at the fracture surface. So in the presentation that I wanted to show you today, I'll be showing you some experiments that we did where we wanted to clarify the role of slip in hydrogen embrittlement by looking at how that slip develops in situ in the scanning electron microscope and how that leads to the initiation of cracks. All right, so the very simple outline of what I'm going to show you today. First, I'm going to describe to you our experiment. Next, I'm going to tell you about the effect of hydrogen on slip. Then I'll tell you about the role of slip in crack initiation, and I'll finally conclude with a few takeaways. Okay, so let's move on to the experiment. The work that I'll be showing you was all conducted on Inconel 725. Now, why Inconel 725? Well, it's really just for historical reasons. When I first started working on hydrogen embrittlement, it was from the sponsor requested to work on Inconel 725. And so I've been working on Inconel 725 ever since then. This alloy is a majority nickel alloy, it's a nickel-based alloy, but it also has a significant amount of chromium, molybdenum, niobium, other elements. It is strengthened by precipitation of gamma prime and gamma double prime phases during heat treatment. It also has a number of other precipitates inside, which I'm not going to go into. And if it does not have hydrogen, if it doesn't contain hydrogen, then it fails in a ductile transgranular manner. So not intergranular brittle, but rather transgranular ductile. And here are some images from a prior work that was done in my group. This is a foil of Inconel 725 that was tested in tension, failed in a very typical ductile transgranular manner. This is a view of the sample surface where you can see areas around inclusions undergoing severe deformation, but not really fracturing. Okay, so the way that we designed our experiments is we created these very small scale tensile test specimens. Okay, so this is an image, just a photograph of one of these things. Those of you who are familiar with American currency will recognize this as a 1 cent piece, a penny. So this sample is basically the size of a cent. The region that we're actually interested in is this box region right here. It's actually very, very small. It's like a tenth of the diameter of a cent, so it's like the size of Lincoln's ear or something like that. If we look from the side, this is looking from the edge onto the sample, you'll see that this region of interest to us is actually thinned. So this gauge section was intentionally thinned so that the majority of the plasticity would occur right there, right? So we know where to look in advance to see all the action. We used physical vapor deposition to deposit a silver thin film on top of this sample, okay? And then that thin film was reformed into nanoparticles that look like this, okay? So this was the reason why we did this is because we want to be able to carry out digital image correlation analysis on this sample during the in situ tensile testing. And so that's how we're going to actually characterize the distribution of slip. To do that, we need a pattern. We need to deposit a pattern on the surface, and that's how we did it. Okay, so we've made the samples, we've deposited the DIC pattern. We then proceed to electrochemical charging. So this is how we introduce the hydrogen, right? These samples are initially hydrogen free. Well, they are nominally hydrogen free. Nothing is actually hydrogen free in reality. So we did test the baseline hydrogen content of this material. It turns out to be about 4/10 weight part per million hydrogen, which is small, but not zero. We then introduce a much larger hydrogen content by electrochemical charging. So in this process, we attach the sample to we basically make the sample to be the cathode in a electrochemical circuit. And the electrolyte that we use here is an acid solution. We charge the sample for 50 hours in this acidic solution, and then we can measure the total hydrogen content using melt extraction. Okay. When we do this, we are not able to charge the sample long enough to arrive at a uniform hydrogen concentration throughout the depth of the sample. Instead, we get something that has a high hydrogen concentration towards the surface, right? Then the hydrogen concentration drops off as you go towards the middle. In the middle of the sample, there's nearly no absorbed hydrogen. And then finally on the other surface, on the other side, there's again this layer of that's rich in hydrogen. In terms of atomic part per million, we get to several thousand atomic part per million at the surface. The experiment as a whole lasts about 4 hours. So that's after we finish the charging, we take out the sample, we do the straining. That takes about 4 hours. During that time, hydrogen tends to outgas from the surface, and so this is our predicted hydrogen concentration at the end of the test. So as you can see, we've lost some hydrogen from the surface, but we still retain a layer about, let's say just over 50 microns deep that has a significant amount of hydrogen, again, several thousand atomic part per million. Okay, so this is what the actual hydrogen concentration looks like through the depth of the sample. Because the concentration distribution is non-uniform, therefore I don't like reporting the hydrogen content as a concentration. Rather, I report it as a surface hydrogen content. So basically, number of hydrogen atoms per centimeter squared, right? Because every surface is covered with a layer that has basically this depth profile for the hydrogen. We test 3 different samples. These 3 samples, one of them has low hydrogen content, one of them has a mid-level hydrogen content, and the third one has a high-level hydrogen content. This is the surface hydrogen concentration expressed as number per centimeter squared. Okay? All right. Once we're done with the electrochemical charging, we then take our sample, we mount it in an in situ tensile stage. This is a picture of that in situ tensile stage. This right here in the middle is the sample. This is a commercial stage that comes from Kamrath Weiss, a supplier from Germany. This stage then goes into a scanning electron microscope. We use a TestScan Lyra microscope. And we then apply a strain rate. We then pull the sample in tension at a rate of about 4 times 10 to the 5th per second. So relatively low strain rate. Hydrogen embrittlement only shows up at low strain rates, so we have to be able to do this at low strain rates. We interrupt the test every 1.3% strain or so, and take an image. So here's what one of the images of the gauge section looks like after something like 10 or 20% strain. What you see here is that there are a lot of secondary cracks, a lot of cracks that have formed. There's something that looks like a main crack beginning to form. There's a bunch of secondary cracks. There's also a lot of slip. This region in the gauge section looks very corrugated, and that's because of all the sort of localized slip that occurs. Here is some information on the mechanical response. So first of all, the stress strain curves. So with no hydrogen, we get a stress strain curve that looks like this. So the sample fails after being pulled in tension to about 40% strain, just shy of 40% strain. All these little dips that you see here are the interruptions that we impose where we actually take images, right? So this is in situ straining. So this is all done in the SEM. Every 1.3% strain, we stop and take an image. That's what the dips are. These other curves that you see here correspond to the low, middle, and high hydrogen concentrations that I told you about before. As you can see, the strain to failure is decreasing as we increase the hydrogen content. These decreases are not as great as what you might be used to seeing from other presentations of hydrogen embrittlement. And the reason why is, again, because the hydrogen content of this sample is not uniform, right? So it's just the exterior surface layers that are charged with hydrogen. The interior is still hydrogen free, right? So this stress strain curve that you see here is not really a property of just one type of material. It's more like the integral response of a layered composite, right? With the exterior parts being brittle and the interior part being ductile. Indeed, if we look at the fracture surface, so this is looking at one side, this is one side of the fracture surface. Here's the other side. You can't, it's obscured a little bit so you can't see. But if you look in the middle, like for example around here, you can see sort of the typical dimpled fracture surface that we expect to see during ductile transgranular fracture. However, if you look closer to the free surfaces, then you see more like a brittle cleavage fracture, which is the sort that we expect to see for hydrogen embrittled materials. So this is, again, just indicating that this sample is not uniform. The hydrogen embrittled part is on the exterior, and then the interior is still ductile, right? Fails by a transgranular ductile manner. So the reason why we did all this is we wanted to observe how things happen in situ. So this is an actual movie of the surface of the sample as we conduct the tensile test. As you can see, there's lots and lots of slip bands that are forming, and eventually cracks form, right? So, playing this forward, we can, see where all the cracks are at the end. But of course, the advantage is that we can also play it backward and try to figure out where the cracks actually started. So let's say here's a little crack. If I keep playing this backward, I'll eventually get to the point where this location closes up, right? So I'll keep playing it backward and maybe just a little bit more, slightly. Okay, so this is where the crack actually initiates, right? So we can actually play this movie back to find the precise moment where cracks initiate, and then we can map those initiation sites to specific microstructure features, and we can also map those initiation sites to particular patterns of slip. Okay, if you look at this image, you see that it's covered with these little dots. Those are the silver nanoparticles that I told you about, which we use for digital image correlation. So what is digital image correlation? Basically, you take two images and you try to spot the differences. So those of you who remember your childhood probably recall, trying to find differences between little cartoons like this. Well, as scientists, as adults, we now do the same thing, but in a more generalized and quantitative way. So let's say I'm comparing two images. I look at two regions within those two images. They have slight differences. By mapping those differences onto each other through a process that I'm not going to go through, we can infer, we can deduce displacement fields. So basically, we can calculate what the displacement fields are on the surface of the sample by comparing two images. From the displacement fields, we can get strain fields. Okay, so here is the a movie that shows you the development of surface strains on the tensile test that I showed you just a moment ago. So the intense bright regions are regions of high local strain, and the blue regions are regions of low local strain. So of course, all of you know that strain is a tensor. So what I'm showing you here is actually the norm of the deviatoric component of the strain. So it's basically showing you, it's kind of like a von Mises strain, if you will. So you can see that there are regions that have, a high localized strain, like this band here, and then it's surrounded by other regions that have low strain. So that's the experiment. So now that I've described to you the experiment, what did we actually find? What did we learn? So let me walk you through that. The first thing I wanted to tell you about is the effect of hydrogen on slip. So one of the main claims of the HELP hypothesis is that hydrogen enhances localized plasticity. So what we want to do is we want to determine whether by changing the hydrogen content, we make the flow pattern go from being uniform to more localized, okay? And we can, now that we have these DIC patterns, these digital image correlation strain patterns, we can answer this question very, very straightforwardly, right? So basically we have this kind of pattern, this kind of strain pattern. And what we want to do is we want to take all the strains at all the different locations and plot histograms, right? So we're just going to bin the strains into distributions, and we're going to plot histograms. And here's what we expect. If the strain is uniform, I mean, just looking at this, you can already see that the strain is not uniform, right? So we don't expect it to be uniform. However, we do want to know whether the degree of localization changes. Okay, so if it were perfectly uniform, then what we would expect is that the distribution would basically be peaked at the average deviatoric strain value, right? We would have a highly peaked distribution centered on the average deviatoric strain. If the strain distribution, however, is localized, then we expect a distribution that looks more like this. We still have the same average strain, right? So this vertical dashed line here indicates the average strain. However, rather than having a distribution peaked at this value, we have some regions with a much higher strain. Those are the regions of localized strain. And then the remaining regions have a lower strain, right? So the way that flow localization works is that rather than having uniformly spread out strains, we have strains that are concentrated in some regions while other regions remain relatively undeformed. Now, in a sort of extreme situation, that might lead to a bimodal distribution of strains, like I'm showing here. In a sort of less extreme situation, these two peaks might be rather spread out, they might overlap, okay? But in any case, you don't expect to see this highly peaked distribution. You expect to see a more spread out distribution, perhaps with shoulders or something like that. Okay, and if hydrogen were to enhance localized plasticity, then these peaks would become more spread out. This sort of this distribution would become flatter and wider as we increase hydrogen, the amount of hydrogen. Okay, so what do we actually see? Here's what we actually see. On the left, I'm plotting the histograms of deviatoric strain at 4 different hydrogen contents. So no hydrogen, low, mid, and high. Okay, all of this data is taken from DIC images at identical strains, which we measure as elongation to gauge length. So all of them at an identical stage in the loading process. Notice that the x-axis here uses logarithmic binning. Right? The reason why I use logarithmic binning is because if I didn't, you wouldn't see anything. You would just see one single peak, very, very sharp peak. But if I use logarithmic binning, then you can see more of a shape to these peaks. And really, all I want to show you here is that there isn't any sort of trend. Right? All of these peaks have comparable width. They have comparable location of the maximum. This is the no hydrogen peak. This is the low hydrogen peak. This is the mid, and this is the high. There's no trend. Okay, we can take these distributions and find the means and standard deviations. Here's the mean plotted as a function of hydrogen content with the standard deviation superimposed as error bars. Again, no trend. All the standard deviations are about the same, regardless of the hydrogen content, and the means are basically the same to within the uncertainty of provided by the standard deviations. Right? So there's statistically they're indistinguishable. So the outcome of this, the conclusion from this, is that hydrogen actually has no effect on flow localization. You have the same amount of flow localization in these nickel-based alloys with no hydrogen as you do with high hydrogen, right? This is something that's relatively well known. We know that nickel-based alloys tend to have slip band formation. This is just a common feature of nickel-based alloys, and it seems that that tendency remains basically the same to within statistical uncertainty, no matter how much hydrogen we add. So does hydrogen have any effect on sort of the more detailed slip patterns in the material? So we conducted a more detailed analysis of this. To that end, we actually correlated the slip patterns that we got from digital image correlation to the microstructure as characterized by electron backscattering diffraction, EBSD. So here's an EBSD image corresponding to this DIC image. You can see that this big crack here has a corresponding big crack here, and this smaller crack here has a corresponding smaller crack here. We actually registered these images quantitatively, so we found fiducial markers on both sides, overlaid them on each other, and then we could basically match all of these regions of intense slip to specific locations in the microstructure. What we find is that slip occurs in both grain boundaries and in grain interiors. We found that the grain boundaries have the greatest slip values, so the slip is more intense in the grain boundaries than in the grain interiors. And we find that all of this is true regardless of hydrogen content. So no matter how much hydrogen we have, these are the features that we always see. Okay, so that's what I wanted to say about the effect of hydrogen on slip, right? Mostly basically that there's essentially no effect. So next I wanted to talk about the role of slip in crack initiation. So here's what we did. I'm zooming in on a particular location within one of our samples. This image here is taken from an EBSD scan. So all the different colors correspond to different grains. This is one grain. This is a sort of thin twin lamella that is intersecting this grain. Here's the matrix of that twin lamella. So basically a grain with identical orientations on two sides of the lamella. And then all the other colors correspond to other grains. In this particular image, a crack was initiated at this location. So basically at the intersection between this thin twin lamella and this green grain that you see over here. This grain boundary right here experienced intense slip. So there was a intense slip along this boundary. And what we did is we characterized the slip, the degree of slip quantitatively just along this specific plane, right? So just looking specifically at this boundary. The way that we did that is we defined a normal direction and a tangential direction, and then we looked perpendicular to that boundary, so basically along the normal direction, and we computed the tangential component of displacement. Okay, so this is a plot now of the tangential component of displacement as a function of location normal to the boundary. Okay, this line that you see here, over here, and over here is a plot of what the actual tangential displacement is as determined by the DIC analysis. Okay, and what you see here is that there's a more or less continuous variation in the tangential displacement as you approach the boundary. Then at the boundary itself, which is the location of the boundary is indicated by this vertical line, at the boundary itself, there's a discontinuity in the tangential displacement, and then it continues again, in a relatively continuous manner, right? So continuous on the edges, discontinuous at the location, right? This discontinuity in the tangential displacement is what we define as slip, right? That's slip. We can actually determine the value of the slip by doing a linear fit to one side, doing a linear fit to the other side, finding the intersection of these linear fits with the plane of the boundary, and then we compute the slip discontinuity as the difference between these two displacements at the boundary plane. Okay, so that's the slip, that's the value of the slip. It's the displacement discontinuity across the tangential displacement discontinuity across the boundary. Okay, we repeated this analysis on every location along the boundary at a variety of different loading stages. Okay, here is that boundary. Okay, we are going to plot the displacement discontinuity as a function of distance from the crack initiation site. So this is the crack initiation site. This is the direction of the coordinate along which we're going to plot the displacement discontinuity. Okay, and here are the plots. So this is the crack initiation site. It's at 0. All right, and here is the earliest time. Right, so basically at the beginning of the test, there's no slip discontinuity, and so basically we have 0 as a function of distance from the crack initiation site. As the time goes on, so basically as we impose a higher and higher load, you see that the slip discontinuity starts to increase. So basically that boundary is beginning to slip, and then it increases a little bit more and more and more and more. Basically, as the loading goes on, the slip increases. However, if you look carefully, you'll notice that the highest values of slip occur something like 10 microns away from the crack initiation site. So the crack initiation site is here, and the highest values of slip occur far away from the crack initiation site, 10 microns or so away from the crack initiation site. So based on this analysis, we see that cracks do not initiate at the locations of highest slip. And this is just an example. We repeated this analysis on dozens of grain boundaries, and we found the same answer, that the locations of the highest slip were not the locations where cracks initiated. Okay, so cracks do not initiate at locations of highest slip. Oops. In fact, quite often we observed situations where cracks initiated at locations with no slip. So for example, here is a crack that we noticed in one of our movies, in one of our in situ straining videos. So this is the crack that we observed at some point. If we play the movie backwards, like I showed you, we can find the moment of initiation. So here's the moment of initiation. Okay, you can just barely see the little edges of the crack sort of starting here and there. And the kicker is that at that point of initiation, the region around this crack has experienced almost no slip. Okay, so this crack initiated with essentially no slip. So this shows that slip is actually not essential for hydrogen-induced crack initiation. Right? Cracks can initiate with no slip. We went through and counted all of the crack initiation sites in all of our tests. And we also determined whether or not a given crack initiation event occurred in the vicinity of intense slip or with no nearby slip. Okay, and this plot that I'm showing you here shows the number of these initiation events as a function of hydrogen content. So this is 0 hydrogen, this is low, mid, and high hydrogen content. What you see is that initially, all the cracks initiate at locations with some slip, right? So this is no hydrogen, no crack initiation events. Low hydrogen, some crack initiation events, all of them occurring in the vicinity of slip. Mid hydrogen content, the majority of the cracks initiate in the vicinity of slip, but not all of them. Right, so there are some events there are some cracks that initiate with no nearby slip, and then by the time we get to high hydrogen content, the majority of cracks initiate at locations with no slip. Okay, so the more hydrogen we have in the sample, the more cracks we initiate with no slip. So hydrogen, if anything, tends to promote initiation of cracks without enhanced localized plasticity rather than with enhanced localized plasticity. Okay, so then what if localized plasticity does not enhance crack initiation, what does it actually do? So we analyzed this in detail as well, and sort of to give you an idea of what it actually does. Here's some images. So on the left, I'm showing you an image where there was a boundary that had intense localized slip. So this right here is a boundary of intense slip. And this particular boundary initiated a crack eventually at this location. Okay? We see that the crack initiation site is not really related to the location of highest slip, but rather to the location where slip is arrested. And what we see quite often is that slip is arrested at locations where a band of intense slip intersects a thin twin lamella. Right, so these thin twin lamella, this right here, this outline, is showing you the location of the thin twin lamella. These tiny little twin lamellae turn out to be very, very effective at arresting slip. And wherever the slip sort of suddenly arrests, that's where cracks seem to initiate. Here's another example where a crack did not initiate, right? So in this case, we have a band of intense slip right here, but it does not encounter any severe obstacle. It does not encounter a thin twin lamella, for instance. There's no thin twin lamella here. Rather, it basically just impinges upon a triple junction. So this is a triple junction between grain boundaries. And rather than being sort of locally arrested, this slip kind of continues along to the next grain boundary, and then it continues along to some other grain boundaries at the next triple junction. So it sort of dissipates gradually rather than being arrested locally. So as far as we can tell, this basically tells us that the main role of slip in crack initiation is actually to generate local stress concentrations, right? So local regions where stress is highly concentrated at locations where there's a very sharp drop in slip. The fact that cracks would initiate at stress concentrations is consistent with the heat hypothesis of hydrogen embrittlement. The other thing that cracks seem to do is, the other thing that slip seems to do is it seems to create regions that are amenable to easy propagation of cracks once cracks have initiated. So here's an example of that. Here's a map that shows you the strain distribution obtained from DIC. This right here, this region right here, is a band of intense slip. We found in this particular tensile test that a crack initiated at this location. Right? So there's a crack initiation site at the end of that band of slip. Okay? Once that crack is initiated, it then propagates along that band of slip. right? So here is that crack after it's grown out a little bit, and you can see that the end of it, that the tip of that crack has propagated out along that band of slip. So the main role of slip and crack propagation in this situation seems to be to reduce local cohesion along the band of intense slip, which again is consistent with the heat hypothesis, right? That cracks are that the role of hydrogen and the role is basically to just weaken the material, making it easier to break bonds. Okay, so with that, I wanted to just summarize quickly what our main takeaways are. So we performed in situ tensile tests on hydrogen-charged Inconel 725. We performed digital image correlation analysis and found that hydrogen has no effect on strain localization. Cracks do not initiate at locations of highest localized slip. In fact, many cracks initiate at areas with no apparent localized slip. Moreover, as hydrogen content increases, more cracks initiate without any nearby localized slip. So if anything, the hydrogen is making it possible for cracks to initiate with no slip rather than with more slip. The main effects of slip on cracking seem to be twofold. One is that cracks tend to initiate at locations where slip is arrested, which seems to indicate that the role of slip is to concentrate stress. And secondly, once cracks are initiated, they tend to propagate along pre-existing bands of localized slip, which seems to indicate that the role of slip is to basically weaken cohesion. Okay, so all of these results, in our view, are inconsistent with the HELP hypothesis, and rather they suggest that other mechanisms, most likely heat, are responsible for hydrogen embrittlement of Inconel 725. With that, I wanted to thank you for your attention, and I'd be happy to take your questions.
Thank you very much, Dr. Michael, for such a nice and informative presentation. So questions from the participants or the audience, they can write even the message box as well.
Excuse me, Dr. Shakur, is it okay also to ask directly? Okay. This is Afruz speaking from HBKU.
Hi, Afruz.
Yeah, sure, please.
Hi, Michael. How are you doing?
Good,
It was an excellent presentation, Michael. Very nice results. Especially showing that strain localization is not happening with the, only due to the hydrogen. I had one question, because we did also work on the same alloy system, and after 18 hours of charging for a precipitation hardened 725, we see almost the whole plasticity goes away. So I got some concern about your hydrogen charging and wanted to double check with you. First of all, you covered the sample surface with this silver nanoparticles. And to me, they can be like kind of interact with the electrochemical hydrogen evolution reaction and kind of reduce the yield of hydrogen uptake to the material. Because first of all, they are rough and good nucleation sites for the bubble instead of atomic hydrogen. And the silver is also known to have different hydrogen evolution reactions. So one thing I would like to know, what do you think about that? Have you think about this or not? And then if you have measured the hydrogen content, you showed some numbers, but I think they are thermodynamic calculation based on your over potential. Am I right?
So Afruz, very good point. I think that one of the weaknesses of prior investigations is that they did not measure hydrogen content. However, we did measure hydrogen content. We used melt extraction to measure total hydrogen content in all of our charge samples. So what you saw there was not a thermodynamic calculation based on overpotential, but an actual experimental measurement of hydrogen content. The only part that we calculated analytically was the penetration depth. And the way that we did that was basically just using literature values of hydrogen diffusivity. Unfortunately, we don't have diffusivity values for Inconel 725, so we use diffusivity values for other nickel-based alloys, Inconel 718, which are very well studied. So, you know, and you know, they're all pretty comparable when you look at different precipitation hardened nickel-based alloys. So, but the total hydrogen content is experimental, right? So that's one thing that I was very, very keen on in this study, that I didn't want to assume how much hydrogen we had. I wanted to actually measure it.
So you did a hot extraction measurement.
Correct.
What about then silver nanoparticles and their, or this silver particles, not nanoparticles?
I was concerned about it at first, mostly because, you know, silver in many ways is similar to copper, right? It can act as a diffusion barrier, right? It has a relatively low hydrogen solubility. So if we had a continuous layer of silver on the surface, then I think that would have reduced the uptake of hydrogen. However, it appears that after reforming, that silver has really, you know, balled up very nicely into nanoparticles, leaving behind no continuous film on the surface, right? So the hydrogen uptake occurs through the silver, through the, you know, regions of the surface that are in between the silver particles, exposed, you know, directly to the electrolyte. And, you know, as far as we can tell, there's basically no effect, no significant effect of the silver nanoparticles on the hydrogen uptake. But this is
Excellent.
definitely a good question. You know, I was also concerned about that at first.
Thanks.
So we have one more question from Dr. Hassan. Dr. Hassan, can you please directly ask question from Dr. Michael?
Yeah, hello, Dr. Michael. This is Mohammed Hassan from Center for Advanced Materials. So very interesting, very nice topic actually. So I just wondered, have you thought about considering applying the same thing for more soft materials like polymers, for example? Would that be the case? Would you see the same phenomena in polymers, since polymers are the coatings, as you know?
I wouldn't assume that what we found in Inconel 725 carries over to other alloys, much less other classes of materials like polymers. I think that the significance of these results for materials other than Inconel 725 is that there are better, more quantitative ways of determining whether slip plays a role in embrittlement, rather than, you know, post-mortem analysis of fracture surface, right? And this is, to me, has been one of the frustrations of, you know, dealing with hypotheses and theories of hydrogen embrittlement, is that they always seem to be based on examination of post-mortem samples, right? But you can't really tell what's going on unless you look in situ. And so I think that while the conclusions that we have here wouldn't necessarily carry over to polymers, I think that the methods that we used may very well carry over. So you could do, for example, an in situ tensile test with you know, with you know, some kind of a pattern deposited on the surface to let you measure the local strain distribution.
Yes. Yes, and speaking of this, actually, if we meant to transfer the method, so in your case, you stop at 1.2 strain percent, and then you take an SEM picture and redo it again and again. I don't know if we can do this with polymers. You know, polymers would relax during that time, so you might have something. You know, the stress relaxation. It might not work. Maybe we have to think about like some better way.
Yeah, but I think that that's a question about the properties of polymers rather than about the efficacy of the test, right? Because if we had done this test at a higher strain rate in Inconel 725, we also would not have seen hydrogen embrittlement, right? So So the test has to be designed to target a range of strain rates and strains that actually exhibit the phenomenon of interest, right? If the phenomenon of interest doesn't occur at those strain rates, well, don't do it at those strain rates.
Yeah,
Do it at a different strain.
you are right. We can control the relaxation time. Yes, we can think about the stress relaxation time for the polymer. Thank you. Thank you so much.
Right.
Thank you.
If no more question, then we can thank Dr. Michael for sharing his great expertise with us. And once again, thank you very much for staying with us. Thank you very much.
Thank you. Have a good day.
Thank you very much. So
Thank you, Michael.
Now we move to our second presenter, who is Dr. Ehsanul Haktoor from King Fahd University, Saudi Arabia. Let me introduce Dr. Ehsanul Haktoor. He's working in the area of materials and electrochemistry at Mechanical Engineering Department, KFUPM. Before joining KFUPM, he worked as a senior research engineer in coating research in Coating and Corrosion Research Center of Samsung Heavy Industries, South Korea. Dr. Ehsan's research focus is mainly the development of new corrosion and wear resistance materials to overcome material degradation challenges in different industries. He is conducting in-depth, in situ, ex situ passive film investigations to understand the role of oxide films on metallic alloys in terms of their oxide structure, composition, and stability. Currently, Dr. Ehsan is serving as a director of ME Corrosion Lab and also an affiliate of the Interdisciplinary Research Center for Advanced Materials at KFUPM. He has published and presented his work in reputed journals and conferences. He is recipient of the Excellence in Teaching and Excellence in Student Advising Awards at KFUPM. Today, he is going to share us with the title Erosion Corrosion Performance Evaluation of Carbon Steels. Please welcome Dr. Ehsanul Haktoor.
So, can you hear me?
Yes, we can hear you.
I can't hear.
Dr. Ehsan, can you share your screen with us?
Dr. Ihsan,
I think Dr. Ehsan has some problem.
Dr. Ihsan is here.
Yeah, Dr. Ehsan, can you hear us?
Dr. Ihsan?
Hello, Dr. Ehsan, can you hear us?
Dr. Abdushakur, if you want to proceed with Dr. Sarah, and we can switch between Dr. Sarah and Dr. Ihsan.
Okay, then sorry for the inconvenience. Then we can go to Dr. Sarah. She is with us. Let me introduce the Dr. Sarah. Dr. Sarah, are you ready? Hello? Noor Badr, can you hear me?
Yes, doctor, I can hear you. I think Dr. Ihsan and Dr. Sarah is not here yet. Just 1 minute, I will check with Dr. Ihsan.
Hello, I am here. If you want, I can start the presentation.
Yeah, it would be great. Dr. Sarah, let me introduce you so that we can skip Dr. Ihsan. So our next speaker is Dr. Sarah. She is holding a senior assistant professor position in the Department of Mechanical Engineering at Polytechnic University of Milan. She received her PhD in Mechanical System Engineering from Polytechnic University of Milan in 2011. Following her PhD, she held multiple research associate and postdoctoral fellow positions at University of Cambridge, UK, Harvard, MIT, Division of Health Sciences and Technology, and Harvard Medical School. Her major research interests are developing mechanical surface treatments and coatings and studying their application in improving structural integrity of metallic metals. She also works on different thermal and kinetic energy-based additive manufacturing technologies. She has been awarded the ASTM International Additive Manufacturing Young Professional Award 2021, Best Talk Award in the first European Conference on the Structural Integrity of Additive Manufactured Materials 2019, and Young Scientist Lecture Gold Prize in the 10th International Conference on the Surfaces, Coating and Nanostructure Materials 2015. Today, she will talk about application of surface processing techniques for additive manufacturing towards improved corrosion and fatigue. Please welcome Dr. Sarah.
Thank you very much, Dr. Shakur, for the nice introduction. I would like to thank you and all the organizing committee for giving me the opportunity to talk about my recent research that is mostly focused on surface processing of additive manufactured components and parts towards improving their performance, especially under cyclic loading. So additive manufacturing, I'm sure you have heard a lot about it, and many different technologies have been devised for additive manufacturing of metallic materials. One issue that is common between all these technologies is the surface quality that is far from being regular and acceptable for many applications. Here you can see some images from different technologies of additive manufacturing, selective laser melting, electron beam melting, and laser MIG arc welding. What you see, the features are totally different between the technologies, but still you see a lot of irregularities, partially melted powders, staircase, stepwise, let's say, features, and a lot of, let's say, randomness in terms of the surface quality that would affect a wide range of applications that could be corrosion, wear, fatigue properties, any contact if these parts are going to be assembled with any other part, or even the aesthetic features are highly affected by these uncontrolled features. So you see that the technologies are giving very different, let's say, surface morphologies, but even in the same technology, as we play around a little bit with the parameters, you see again there is a lot of variation that is not really controllable. So here for selective laser melting, we have been changing, let's say, the energy densities. Here the powder diameter has been changing, and here the laser powder. And you see each change in the parameters of the process is causing a lot of variation and randomness in these agglomerations that are on the surface of the parts. So that would necessitate application of post-processing in order to get a more regular surface morphology, depending again on the final application of the part. In a recent review, we have been studying all the possible post-processing techniques that have been applied to additive manufactured parts and had categorized them in those that are based on removing material, so removing a very thin layer of material from the surface in order to make it more smooth. It could be mechanical treatment, laser-based treatment, or chemical treatment, and sometimes even hybrid treatment, combinations between them. Some other material post-processing techniques are based on not removing any material, but trying, for example, to exert some severe plastic deformation on the surface in order to flatten out these surface irregularities. They are rolling, bead blasting, shot pinning, cavitation pinning, and so on, and some other thermal-based or laser-based treatments, again, like laser shock pinning or laser remelting or polishing of the surface. And then the third category is coating. That would could be used also to surface functionalize of these parts, but at the same time we will have the problem of the interface. So again, depending on the quality of the surface and the final application of the part, one would could select one of these post treatments in order to apply to that specific additive manufactured parts. In our research, we have mostly focused on mechanical surface treatment, and specifically shot pinning. If you have heard about it, it's a widely used mechanical surface treatment used in the industry, especially in automotive and aerospace industry, for inducing compressive residual stresses through impacting a large number of high energy shots that can be ceramic shots or steel or different materials that would impact the surface of the substrate, would cause plastic deformation on the top surface. And because of this equilibrium of the elastoplastic deformation of the top surface and the underlying one, we will have compressive residual stresses. We can have microstructural changes in terms of course, increasing the dislocation density, in some cases phase transformation, and in general work hardening and increasing the hardness of the top surface layer. As a side effect, we have also surface roughness increasing because of shot pinning. But again, we will see in the next slide how the surface morphology of a shot pinned additive manufactured part would be different from the as-built one. In our research, we have also worked on playing around with the parameters of shot pinning in a way to induce also grain refinement, to have an interface-free gradient starting from nanostructure, ultrafine structure, and then going down to the original, let's say, microstructure of the material. So again, by selecting the parameters of the shot pinning based on the target material properties and the target application, we can play around a little bit with these effects that are the typical effects of shot pinning. So what we did is that we tried to combine different post-treatments, thermal post-treatments and mechanical post-treatments, in order to optimize the performance of additive manufactured parts, in this specific case, laser powder bed fusion parts for fatigue performance. These parts in as-built configuration have very high tensile strength, very high hardness, but at the same time, they have a lot of, they are, let's say, prone to have a high density of defects, depending again on the parameters of the process and the process itself. And they mostly are characterized with high tensile residual stresses, low ductility, and again high roughness that I talked about in the first slide. These parameters would directly affect the fatigue performance of these parts. So we tried to apply different post-treatments, including heat treatment, shot pinning, and sand blasting, in order to see how much we can modulate and improve the mechanical performance of these parts on the cyclic loading. So the series of the samples that we were studying in this specific research was the as-built configuration for reference. Then we just heat treated sample, sand blasted sample, shot pinned sample, and then combination of heat treating and sand blasting, heat treating, and shot pinning. Just to give you an idea about the difference between sandblasting and shot pinning, if you're not familiar with that, the concept is always the same. So we are impacting the metallic material surface with a high density of particles that are accelerated by compressed air. The difference is that in sandblasting, the size and the morphology and quality of the particles is not much controlled. The whole process is manual, as you can see in this image, so there's much less control. Let's say generally this treatment is used in the industry for descaling and removing the corrosion products from the surface of metallic parts. So there's not much control on the kinetic energy of the process that is going to be transmitted to the substrate. While in case of shot pinning, everything is robotized and automatized. So we have, let's say, very fine control on the size of the shots, on the direction of the shot, morphology of the shot, and the energy and the velocity of their impact. So first, let's see the results for the effect of the heat treatment. So here we have a different cross-section of our samples perpendicular to the build direction and parallel to the build direction before heat treatment, so in the as-built configuration and in the heat-treated configuration. Again, transversal section and longitudinal section. You see that before the heat treatment, we have these scan tracks and all the features that are related to the tracks and the movements of the laser source, the melting pool and the boundaries of the melting pool. In these SEM images, we can even much better see the inhomogeneity that we have in the grain size between, let's say, the two neighboring melting pots, pots. And then here, after the heat treatment, you see that these scan tracks are mostly eliminated both in transversal section and also in the longitudinal section. So the heat treatment itself has a considerable homogenizing effect on the microstructure of the material. The silicon particles are much more homogeneously distributed in the aluminum matrix. Here we are talking about the aluminum Si10 magnesium alloy, which is one of the most typical aluminum alloys for additive manufacturing. So the heat treatment is promoting a lot isotropy also in the mechanical properties, because as you can see in the as-built state, we have substantially different features in the as-built in the transversal and the longitudinal direction of the as-built sample. So the heat treatment is helping a lot with eliminating those features and the effect of the direction. Here you can see again the three-dimensional, let's say, cube for optical microscope images, SEM and EBSD, again confirming that heat treatment is resulting in slight grain largening, let's say coarsening of the size of the grain, but it's also improving a lot the distribution, the homogeneity and isotropy of the structure. We performed tensile tests on the samples before and after heat treatment. Also, in this specific configuration, we had some areas in the build area where we had more than one laser source working simultaneously. So we evaluated also the effect of simultaneous or more than one, let's say, lasers in working in different zones by taking some tensile samples that were made exactly in that area. And we eliminated, let's say, the hypothesis that more than one laser working at the same time could have affected the mechanical properties of the sample. As you can see, the dashed line and the solid lines, which are for samples taken from the overlap and non-overlap area, are quite the same. But what is interesting is that the heat treatment is considerably increasing the ductility of our samples. And that is to the extent of losing a little bit of the strength, but the ductility, of course, is more than doubled, almost 3 times higher compared to the as-built configuration. And now going back again to the to the morphology and the issues that I was talking about, and was, let's say, the whole motivation of the study. Here you can see the SEM image of as-built surface, where we have a large, let's say, random distribution of the partially melted particles that are adhered to the surface. And here you can see the, again, top surface SEM observation of the shot peen samples and sandblasted samples, before heat treatment here on the left and after heat treatment on the right. So you can see after the shot peening, we have the typical, let's say, overlapping dimples that are created by multiple impacts, but the surface is much more regular compared to the original as-built samples. Sandblasting also is resulting to a better surface, but still there were some residuals. If we get closer, there were some residuals of these partially melted powders that were still remaining in the sandblasted samples, while for the shot peening, where we had higher kinetic energy, that was not the case. We quantified also the roughness parameters, and as you can see here, we have quite high surface roughness in terms of the arithmetic mean parameter and the root mean square for the as-built and HT heat-treated samples that are the same, while for the sandblasting and shot peen samples, we have a considerable decrease in the surface roughness. Apart from that, you see the scatter band is also decreased a lot, so we have a lot of irregularity and randomness in case of the as-built configuration, while for shot peening, the scatter is much less. The heat-treated samples after shot peening had higher roughness. That's because they were more malleable and more ductile and more deformable. Also, in terms of the porosity, these post-treatments were helpful because the shot peen samples and the sandblasted samples showed some pore closure, at least the ones that were very close to the surface, so resulted in a general slightly lower porosity with respect to the as-built sample. And then we performed rotating bending fatigue test on these samples, all the 6 configurations, so as-built, heat-treated, sandblasted, shot peen, and then combinations with shot peening. And interestingly, we observed over 250 times fatigue life increase after sandblasting and shot peening in our samples, and that is related to the collective effect of more homogeneous surface roughness, the higher ductility, the compressive residual stresses. And in this case, we are not talking much about the grain refinement because the parameters that we had selected for the shot peening are not that effective in terms of grain refinement. The fractography images showed that the fatigue cracks were still starting from the surface, so still the surface is let's say, the most critical part, especially under rotating bending fatigue strength, where we have a high gradient of the stress on the surface. But being able to homogenize the surface roughness with respect to the as-built configuration helped us a lot to increase considerably the fatigue strength of the material, getting close to the range for materials that are fabricated with standard manufacturing technologies rather than additive manufacturing. So I talked about the effect of the treatment and the effect of the treatment process on surface quality. But there is another parameter again that is causing a lot of variation in additive manufacturing parts in terms of surface morphology. So we are always bragging about the potential of additive manufacturing for being able to make very intricate geometries. But with that comes a problem, and that is, as we have intricate geometries and as we are changing the direction of the surfaces with respect to the build direction, we will introduce a lot of, again, irregularity and variability in terms of surface quality. Here you can see, for example, in an U-notch geometry, considering a build direction that is in the, let's say, vertical direction, we will have 3 different zones with 3 different surface morphologies. In this upper skin area, we will have lower surface roughness. Then we have the surface of the notch that is getting, let's say, more parallel to the build direction. And then we have the highest surface roughness, as you can see in this schematic, in the down face area. So we will, in this area, we are constantly changing, let's say, the surface morphology, and that would again affect the functionality of these components depending on the final application. In this specific case, we were more interested in on the effect of these features in on fatigue performance. So in order to study the effect of these processing techniques, also on geometries that are, let's say, far from the smooth standard geometries, we designed these U-notch samples and tried to apply again the combination of the heat treatment and shot pinning on these samples in order to see how we can improve and get a more consistent surface morphology also in more intricate geometries with these post-treatments. In particular, these are the two surface treatments that we applied in terms of shot pinning using cast steel and ceramic shots. For the second option, we used smaller shots in order to make sure that we are arriving to the notch root to get a more smooth surface morphology. Here you can see again.
Dr. Sarah, can you conclude? We are, having time limitations. Sorry for the interruption.
Sure, of course. I will try to conclude within few slides. So here you can see again the variation of the surface softness from the top surface to the notch and to the bottom, and the images that we have for after shot pinning, where we are getting to a much more regular surface morphology. Again, here you are seeing the effect of the process, the original surface with a lot of deviation in terms of high surface softness, and then much smoother surface that we obtained after shot pinning, also quantified here in terms of the surface roughness parameters. And finally, the fatigue performance. Again, also here we observed that we were able to eliminate even the effect of the stress concentration because of the presence of the notch with proper shot pinning. So the shot pinning was helping to induce compressive residual stresses, reduce the surface roughness, and lead to eliminating, or let's say almost masking, the detrimental effect of the presence of the notch on the whole surface. So I wanted to talk about some numerical modeling that we have been doing also about shot pinning. Just briefly, we have modeled the simulation also starting from the very rough surface of as-built additive manufactured parts, and have tried to kind of predict the effect of the process parameters in terms of shot pinning on the final roughness parameters that we can get. So with this numerical simulation, we have been able to compare and validate the simulation with experimental data, confirming that we are able to get very close to the real surface softness parameters that we can get by shot pinning. And then applying analytical approaches, we have also predicted the effect of the shot pinning on the fatigue performance of the part. So we will be able to kind of optimize the process parameters before the experiments in order to use the simulation as a tools for predicting the effect of the shot pinning in terms of the fatigue performance of additive manufactured parts. So with that, I would conclude. I would just like to thank the contribution of the postdoc, PhD student, graduate students, academic and industrial collaborators that have been contributing to this work, and I would be happy to answer any questions if you may have.
Dr. Shakur, you're muted.
Thank you very much, Dr. Sarah, for such a nice presentation. So we can have one question from the audience because we have time limitations. If not, then we can move to our next speaker. Once again, Dr. Sarah, thank you very much for sharing your great knowledge with us. Thank you very much.
Thank you. Thank you for the invitation.
So we can move to Dr. Ehsanul Haktoor. Professor Yukshin, we have one speaker left. Maybe after him, we will give you a chance, right?
Okay, no problem.
So let me introduce Dr. Ehsanul Haktoor. He is working in the area of materials electrochemistry at Mechanical Engineering Department, KFUPM, Saudi Arabia. Before joining KFUPM, he worked as a senior research engineer in Coating and Corrosion Research Center of Samsung Heavy Industries, South Korea. Dr. Ehsan's research focused mainly on the development of new corrosion and wear-resistant materials to overcome material degradation challenges in different industries. He is conducting in-depth in situ ex situ analysis of thin films to understand the role of oxide film on the metallic alloys in terms of their oxide structure, composition, and stability. Currently, Dr. Ehsan is serving as a director of ME Corrosion Lab and also an affiliate of the interdisciplinary research of IRC Advanced Materials at KFUPM. He has published and presented his work in reputed journals and conferences. He is a recipient of Excellence in Teaching and Excellence in Student Advising Awards at KFUPM. His today's title of presentation is Erosion Corrosion Performance Evaluation of Carbon Steel. Please welcome Dr. Desan.
Oh, thank you very much, Dr. Shakur. Can you hear me?
Yes.
Okay. Because I'm very sorry, there was some issues, I think, in my connection. I don't know why. So I was kicked out from the schedule. So I hope it will work well.
Yes,
so,
it works well.
You can see the screen also.
Yes. Please go to the presentation mode.
I am in the presentation mode, I think. Okay. So if there was there is any issue, just please let me know. Okay.
Just Dr. Ehsan, I'll just update. If you go to the share, share the right screen.
If I go to the just a second. If I go to the share, I need to share the screen, you mean? Not the application.
Right now presentation mode.
Oh, just a second. Okay. What about now?
Excellent. Please go ahead.
Okay now? Okay. Thank you very much, Dr. Shakur, for the
Dr. Ehsan, we cannot hear you.
Yes, please. You can't hear me?
Yes.
You can hear me or no? You can hear me?
Yes, Dr. Ehsan, we can hear you. Please present.
Okay. Because there was some communication. So anyhow, the outline of the presentation is that we will discuss a couple of things here, some background of this research activities. Based on this, some background, we have as a group here in the department in particular and in the university, we figure out some objectives a few years back. Based on those objectives, we try to develop some facility at KFUPM, and then we will briefly touch some of the research activities which we have conducted and which are ongoing. And at the end, we will see what is the plan for the future. So probably most of you are well aware of the problem of erosion and erosion corrosion in engineering systems. There are a lot of issues in different industries. This section is about oil and gas. So let's say in oil and gas also there's a lot of issues related to erosion corrosion, one way or the others. We have machine components, impellers, pumps, etc., the pipelines, all of them. They are affected by this process of erosion corrosion. And if we see some recent surveys about the cost of corrosion, there are a lot of stuff here. But in case of internal corrosion of the pipelines or the components, is a huge value here. Not all of that is related to erosion corrosion, but there's a big amount of contribution from the erosion side is there. In the kingdom also we have, like here is mentioned about the US, but in the kingdom also we have a lot of, the pipeline infrastructure. A lot of issues are there. So we conducted some surveys over the years based on the discussions with the industry, also based on ongoing research activities here and there. we figured out that there are a lot of issues still there, though the research is ongoing over the past many years in this area. A lot of work has been done. A lot of things has been developed, but still there are some issues. For example, how the material hardness is affecting the erosion behavior and erosion corrosion behavior. What is the effect of the solid particles in the pipelines, how the ductility effects are there, how it affects the corrosion rate, etc., and erosion in particular. So there is a lot of space available for the research activities which can help the industry. Similarly, the second part of my presentation will briefly touch the CO2 erosion corrosion issues also. So in CO2 also there are a lot of issues, a lot of work is being done, a lot of models have been developed also, but still there are a lot of issues related to the impingement angle, velocity considerations, pH effects, and so on. So based on this, we thought that it would be good to develop some. There was a demand as well from the industry around us, and we thought it would be good to develop an in-house erosion corrosion database. So based on this idea, we especially started working around 6-7 years before in this area, that let's try to build our own erosion corrosion database for a variety of materials, starting from carbon steel, aluminum alloys, and stainless steels, etc., in different environments, starting from considering the different industries, oil and gas, desalination, etc., and also at different, considering the variables. We are not focusing so far actually on the pressure side, but at different temperatures, especially angles, velocities, etc. So try to develop our own in-house erosion corrosion database, which will help us to develop some correlations, and we will use those correlations to develop some erosion corrosion prediction model for the local needs. We are not done yet, but I think we are moving nicely in this direction. We have recently established some erosion model. Still a long way to develop some erosion corrosion model, but we are going in that particular direction. So then we started developing our lab here. We got one very good equipment, that is air jet erosion tester facility in the lab for the solid particle erosion testing at different angles and different velocities. We have lucky to develop this very nice beautiful loop, actually made of 316 stainless steel for the erosion corrosion testing. We designed it with a lot of effort in a way that we can do a lot of things to save our time. There are 2 testing chambers there. We can do at least two experiment at 2 different velocities at 2 different angles. Here also inside we can maintain the angles from 15 to 90 degrees. So a loop testing facility was also established maybe 3 years or 4 years back, and then we started working in this direction. So the first part of some of the activities which we have conducted, the first part is related to evaluating the solid particle erosion behavior of different metals under different conditions. So as I mentioned in the beginning, we figured out that there is some gap, there is some contradiction in the literature, that how the behavior, how the hardness of the materials affects the performance in terms of the erosion behavior of the materials. So we selected 4 different types of metals: carbon steel, stainless steel, and aluminum, with the different hardness values, because the idea was that we want to relate and we want to see comprehensively how the hardness and the ductility of the material that affects the solid particle erosion behavior of the materials. So based on this, a lot of experiments were performed at different velocities, starting from 30 to 100 meter per second at 6 different angles for all these different metallic materials. And some of the results which we got were very interesting results. For example, the figure shows here the erosion rate versus angle, and what we notice for all 4 different alloys, I think the angle is here, the velocity here is 60 meter per second. So what we notice from this figure is that the peak erosion rate in all these 4 materials was around 15 degrees somehow, except for 1020 carbon steel, which is around 30 degree. But these between 15 to 30 degree, this erosion rate is usually typical of ductile metals. Usually the ductile metals, their peak erosion rate is observed at lower angles because the shear forces are quite significant at those lower angles. So irrespective of the material type, all of the materials, they showed the highest erosion rate around 15 to 30 degree, then at this velocity of 60 meter per second. Another thing which is important to notice here is that the highest erosion rate in this case was observed for 310, followed by 1020 carbon steel. And if we see go back to the previous table, the 1020 steel, 310 was the highest, having the highest hardness. So bulk hardness of the material, not the surface hardness. So the bulk hardness of the material, it shows some link between the erosion rate and the bulk hardness of the material. So the main point here was all of the four materials, they are behaving in a ductile way because the peak erosion rate is observing between 15 to 30 degrees. So next figure. We then compared the erosion rate at different angles, and for all different materials, we have 1, 2, 3, 4 different materials. We evaluated them at 3 different velocities, starting from 30 degrees, 30 meter per second to 100 meter per second. One thing we notice is, which is, by the way, is a straightforward, that as we increase the impingement velocity or the impact velocity in all these cases, the erosion rate was increasing for all samples. So starting from 30 to 60 to 100 degrees, 100 meter per second. In all cases, the trend remains the same. In all cases, the peak erosion rate was observed 15 to 30 degree. So with the increase in kinetic force which we are applying on the system, the erosion rate was increasing. We cannot say that this was independent on the angle, but does depend on the material or the substrate performance. Because if we observe here 1020, the maximum erosion rate which we observed for 100 meter per second was around 0.25. But in the case of stainless steel, we are having a little bit higher at 100 meter per second. Similarly, for aluminium, which is worth discussing, is that in case of aluminium, the highest erosion rate was the lowest, which was around 1.12 milligram per gram. So that means all these three plus minus, they have similar hardness. Aluminium is having around it's 1 to 3 ratio. So aluminium is around 80, and all three other materials have a high hardness around 200. So that shows that as the hardness increases, that means the erosion rate behavior of the material erosion rate of the material is also increasing. Okay, on this slide, we just try to compare them. All the materials, for example, 30 meters per second, all 4 different materials, 60 meter per second and 100 meter per second, all 4 different materials were compared together. That the trend remains the same. And the conclusion is that as we increase the impingement velocity or impact velocity, the erosion rates were increased significantly. However, the aluminium in all cases, which is the most ductile among all these metals, showed the lowest erosion rate. That means that there is something in the case of aluminium, or there is some linkages between the hardness of the material and the erosion behavior of that particular material. So we try to look into the surface morphologies of these 3 different materials, and we found that there is a significant difference the way the forces are acting on the surface of the material. For example, this is 310 stainless steel. This is 102 carbon steel. So at 15 degrees and 90 degrees, we took 2 different angles. And we see that at 15 degrees, in both cases, in 1020 also and 310 also, we have different types of surface removal or degradation. We are having some extruded regions there. We are having some deformation scratches there. We can put a different names. We can say in different names, but the behavior here is quite different as compared to the 90 degree. So as I mentioned before, that at the lower angles, mostly it is the shear force which is acting on the material. So these ductile material at lower angles, they are forming sort of lips are being formed, and when the successive impacts of the erodent particles are being are there on the surface, those lip removal is continuous. So more material removal is there at the lower angle as compared to the higher angles. Same goes for aluminum also. So these two are the high hardness material. Uh, However, this one is the for the aluminium. See total different surface observation in the case of aluminium. We have sort of flake formation rather than the lip formation and deformation scratches. A wavy structure is there at low magnifications. So it seems here that the shear force rather than um, removal of the surface by the lip formation like here or the deformation scratches is sort of a plastically deforming the material. It's a sort of dissipating the stresses rather than removing the material from the surface. So a total different sort of observation was observed in the case of aluminium. So all four of them are ductile materials, but the hardness value is different. We know that on the microstructure level also we have different, the structure is there, but because of this behavior of the surface, because of the bulk hardness of the material, different observations were different material removal were observed. So the conclusion of the part one is that we observed that the erosion rate was directly proportional to the bulk hardness. This is not that straightforward, by the way. We are still working on this. There are many other things which has to be incorporated in terms of the phase morphology, in terms of the grain size, structure, orientation, etc. But in general, this is related to the bulk hardness. We found a mechanism based on the surface morphology observation that we have sort of a lip formation, ploughing at the lower angles as compared to the higher angles. So that helps in more removal of the surface. Increase in velocity resulted in increase in erosion rate, and we observed the main, peak erosion rate around 15 to 13 degrees in all specimen, irrespective of what kind of material it was. Quickly going to the second part. So we have done this study. So still we are working on solid particle erosion. We are evaluating different sort of coatings on the substrate materials. Some questions are still there to address. So the work is ongoing, but this was the initial study we conducted on this subject. Secondly, recently we did some evaluation on the API X65 carbon steel in the CO2 environment. And there's a lot of data again in case of CO2 environments. CO2 is there all around. A lot of work is being done. By the way, H2S is more problematic for us, but experimental facilities for the H2S is not that easy. But even in case of CO2 corrosion and CO2 erosion corrosion, there are a lot of things which has to be still resolved. So we are working on this. This is the first phase of the investigations in which we investigated the API X65 under different conditions. We got some issues with the industry around us, so we want to figure them out. We use the loop here, and a comprehensive study was conducted again here. A lot of specimens were tested at different conditions. 3 different angles mainly were focused here, but we tried actually 6 also, reporting here 3. We tried to maintain the pH 4.5 to 5.5. This was also very challenging because we in this experiment, rather than changing the pH, there are a lot of literature in which they change the pH of the solution by adding some other chemicals like NaOH, HCl, etc. But we thought that it would be better to control the pH by dissolving the CO2 into the solution. So we tried it. We wanted to go a little bit lower sides, but because of some experimental limitations, our equipment limitation also, we couldn't go. So we maintained these 3 pH values, and then we tried it without sand and with sand at 3 different pH and 3 different velocities. Okay, let me skip this one. We calculated the hardness of the material and others, composition, etc. One of the very important parameter we are well aware of this is the sand particles. So we collected also the sand particles of different morphologies from the locally from here, and the sand particles used in this investigation were of different size, angular shapes, but the average size was around 190 micrometers, something like that. Okay, so let me just skip them. So once we did these experiments at different pH values, pH 4.5, pH 5.0, pH 5.5, three different pH values, and we are reporting here for two different velocities, 8 meter per second and 16 meter per second. Oh, the samples were, you see, of very different colors, and the impingement, the point where the fluid was impinging, that morphology was also quite interesting here. Different coloration was there. So we try to look into this to get some evidence what's going on the surface. Try to summarize here that the coloring was dark coloring was observed almost in all images without sand. But when we have the sand, dark coloring was observed only for pH 5 and 5.5. Coloring intensity was also changed. Actually, it has very I mean, later on we'll see that it has very interesting things to correlate with. The scars, number of scars were increased as velocity increased, but with sand they were not that visible. So seems like their velocity was decreased. So we tried to figure out what these different coloration is, and we conducted some other investigations like. XRD was conducted to see if, the surface composition, what kind of phases are there, and so on. We found that remember that most of our experiments are at room temperature.
Prasan, can you conclude, please? Because we have time limit.
Yes, just a couple of minutes. Yes, I will conclude. So we figure out that mostly the surface is having some some iron carbide is there, some iron oxide is there in the form of magnetite. And because there is no carbonate scale, because our most of our all the experiments were at room temperature, and for carbonate stability we need high temperatures. And why we found this iron oxides there on the surface, we tried to link it with the Popix diagrams, and we found that the potential which we are having in our environment was around minus 0.35, something like that. And that temperature, there should be some corrosion of the iron, and iron cations are present there along with some cementite also. So when the iron is corroding, so the remaining skeleton will be only mostly the iron carbide. So that's why these different coloration in the form of iron oxides were there. And some of these oxides, as we increase the pH here, we found that there are two types of layer: inner oxide layer and outer oxide layer. At high pH, the inner oxide layer was very good. Outer was also quite better. But as we are decreasing the pH, obviously the thickness was much more, a little bit more porous. Porosity was there. Detachment was there from the surface also. And when there was a sand, that outer layer, which was just oxide layer, that was not very compact, it was removed. But inner layer was still intact. So the inner layer was the main layer which was causing which was protecting our material there. So to summarize, what the results we got at different pH is that in most cases, this is at pH 4.5 at two different velocities and three different angles. With sand and high velocities, with sand, the corrosion rate was increased. Erosion corrosion rate was increased, but highest erosion corrosion in all cases was observed around 45 degrees. And this is again related to our previous discussion that it is the distribution of the impact of the shear forces and normal forces. So around 45 degrees, that balance was established between the shear forces and the normal forces. Remember, in case of solid particle erosion, the ductile metals, we are having the maximum erosion at 15 degrees or 30 degrees. But now, because we have scales and oxide, so they can be easily removed. The impact is much higher at 45 degrees as compared to the lower angles. So what we concluded in this here is that CO2 erosion corrosion rates were increased as pH was decreasing. Also, we found that highest erosion corrosion was around 45 degrees. As velocity was increasing, in general, the corrosion rates were also increasing. Couple of other things before I stop, that what is the issue now? So based on this these activities, we found that there are a lot of issues. For example, right now, most of our calculations are the weight loss calculations. And there's a lot of issues to remove the samples from here, to clean them, to measure the weight loss, though there are established procedures, but still there is a lot of challenges. So now we are modifying the loop to some extent so that we can measure the in situ erosion corrosion of the materials during the experiment. So we are developing these new cells here. Maybe one of them will change it to measure the in situ. During the working, we can measure the erosion corrosion behavior of the materials. Another thing which is important is because all this effort is to develop some erosion corrosion models, and there are a lot of data is already available. Some models are already there. We are moving in this direction. Recently we published some article related to the erosion model, and the second part is that we need to, based on these expertise, we will be heading towards developing the better erosion corrosion prediction models. This model which we developed for the erosion prediction still not validated, so we are also in the process to validate this. And at the end, I want to thank and acknowledge the department, KFUPM and large, and different projects which helped us to conduct this, especially my students as well. Three of them worked on these projects. A couple of colleagues, Dr. Badr, Dr. Mansoor, Professor Shirazi, we are coordinating with him, and University of Tulsa, Professor Weil. So that's all from my side. Thank you very much. Any questions?
Thank you very much, Dr. Esam.
Thank you very much,
Nice
Dr. Esam,
presentation.
for a nice
So,
presentation.
because of time limitations, I don't think we have an opportunity to have some questions from the participants. So,
Thank you very much, Dr. Shakur and Dr. Bilal, for this opportunity. Thank you very much. Appreciate.
thank you very much. It is really,
Thank you very much.
really
It
our
is
pleasure.
really our pleasure.
Thank you. Assalamu alaikum.
So then
So
we'll
then
move on to
we
our
move
next
on to
speaker.
our next speaker.
Our next speaker is Professor Yuxin Wang. Professor Yuxin Wang was born in 1985. He obtained the doctorate degree of engineering at Tongji University in 2011. From 2010 to 2016, he worked in Professor Gau's group in the University of Auckland, New Zealand. In 2016, he joined Jiangsu University of Science and Technology and was appointed as Jiangsu Distinguished Professor. Now he is the Vice Dean for School of Materials Science and Engineering, Jiangsu University of Science and Technology. His research interests include corrosion and surface protection, powder metallurgy, and magnetic materials. As a project director or main investigator, he led more than 10 national projects in recent years. He has already published more than 100 SCI papers and issued 9 patents, including 3 PCT patents. He is the editor member of the Transaction of Non-Ferrous Metal Society of China and Journal of Central South University. His title of today's presentation is Preparation and Corrosion Resistance of Nanocomposite Coatings Fabricated by Electrochemical Deposition Process. Please welcome Professor Yuxin Wang.
Thank you, Dr. Shakur. Nice to meet you. Okay.
Thank you, my pleasure.
Yeah, so I will stop my video because I don't think yeah, I will do the presentation for my okay, yeah, okay. Is that okay? You can see my PPT or not?
Yes, is this okay, Dr. Yuxin? Can you go to the presentation mode? Yes, here.
Okay, great. Yeah.
Yeah, great.
Yeah, okay. So, yeah. Okay. This is my presentation name and my presentation contents, including 5 parts. The first one, I will do the general introduction. Then that is my new method for the electroplating. and then it's our recently research outcome. Finally, I want to generally introduce our research institute. Yep. The first one is the introduction. Yep. First, as we all know, the metal-based nanocomposite coatings have a wide application fields, including the ocean, military, energy, aerospace, transportation, and mechanics. It can realize the functions of the surface protection, surface decoration, and the surface modification. The better the dispersion of nanoparticles, the better the performance of the coating. The existing fabrication methods is that we're adding the nanoparticles or nanotubes directly into the electrolyte and deposited it on the surface of matrix materials by electrochemical reaction. But the problem is that due to the high surface energy of nanoparticles or nanotubes, it is very easy agglomeration during the preparation process. Then during the preparation process, in order to and then so during the electroplating process, the mechanical stirring, ultrasonic vibration, and other dispersion methods are needed. And the limited performance improvement due to the particle agglomeration. And then during the general preparation process, the high energy will require a high energy consumption and also the high cost. And also during the fabrication process, environmental pollution and the contact damage will caused by the nanoparticles. Recently, one research tendency of the nanocomposite coatings is that the intelligent bionic coating. We can see the lotus effect, and also we can see the shark skin. They have very special surface, and also we can see the packaging. We learn from the nature. We learn from the animals. We can get a different surface, and from the packaging we can do the anti-icing coatings. And our new method, the first method is the so-enhanced electroplating method. This method was developed in the University of Auckland, and I using this method do the research on this method for a long time. So this method is generally combines the soil gel method and also the electro deposition method. Then we can get the so-enhanced electroplating method. The principle is that during the plating process, the transparent soil is added into the electrolyte, and the nanoparticles are formed in situ and co-deposited with metal ions in the coating matrix. The highly dispersed distribution of nanoparticles is realized during the process. And the left image is the deposition process. This is a sketch map of the so-enhanced plating deposition process. And the strengthening mechanism of the nanocomposite coatings is that the high dispersion effect and also the grain refinement effect. We can see the right HRTM images. It is very clearly that the very fine nanoparticles distributed in the grain boundaries. We can see the size is around 10 nanometers. Another method we developed recently is that the direct electro deposition based on anodic oxidation. I think you guys may know the anodization process. It's a very popular process for the metal surface finishing. And when we do the anodization process on the metals, we can get a very fine nanotube arrays. So we can use the nanotube arrays as a mode, and when we do the electrode deposition onto the nanotube, so we can see this picture, and we can also modify the electrode deposition process, and then we can get a very special surface and to achieve different functional properties. So we can get the functional coating. So this is our general sketch map of the electrode deposition based on anodic oxidation. This is another one this is another sketch map we do on the aluminum substrate. We do the anodization on the aluminum substrate, and we can get very fine nanotube arrays. And then we do the deposition from the nanotube. And finally, we do the surface modification, and we can get the white properties. So this picture is the ternary coupling hydrophobic model of aluminum alone. The first one is the convex nickel layer. The second one is the acicular nickel layer. And then we do the low energy modification. So we can get a very good white properties. Then I want to share our research outcome recently. For the soil enhanced electroplating method, this is the plating solution with soil. We can see from this high resolution image, we can see that the 20 nanometer nanoparticles were formed in situ and highly dispersed in the electrolyte. The right image is the dispersion image. We can see the nanoparticles have a very small size, and also the dispersion distribution of nanoparticles can be maintained for a long time. This is our advantage of the soil electroplating. And recently we do the copper phosphorus titanium oxide coating. This is a soil enhanced one. We can see the first image is the copper, is the cobalt phosphorus coating. They have a very clear boundary. Yeah. Then we add some of the we add a proper amount of the titanium soil into the coating, and we get the nanocomposite coating. We can see a very clear coating on the surface. And finally, we do, in order to see the nanoparticles, we adding 50 milliliter per liter titanium oxide soil into the coating. We get this one, yeah. And the right one we can see the right image we can see the hardness. When we add the 12.5 milliliter per liter titanium oxide, we can get a very high hardness. Yeah. And the bottom image is the high resolution TM image. We can clearly see the nanoparticles distributed in the ground boundaries. This is the corrosion resistance images. We can see the corrosion resistance, corrosion properties of the coating is the same as the mechanical properties due to the fine distribution of the nanoparticles. This is the cross section of the coatings when we add too much soil into the coating. We can clearly see the large titanium particles, and also we can see the pores. Maybe this is the reason why the corrosion resistance was decreased. We also investigate the copper, tin, zinc, titanium oxide coatings. We do different coatings with a different amount of the soil. you can clearly see the different surface. When we adding more, the more so added, we can see the more wounds on the surface. We also see a same tendency on the micro hardness and also on the corrosion resistance. Second part is the electrode deposition based on the anodic oxidation. This is the aluminum. We use the aluminum as a substrate, and we do the anodization. We can get very fine nanotubes areas. This is a porous structure, and then we do the nickel phosphorus deposition onto the nanotubes, and we get the nodular structure. The red images are the zincated nickel phosphorus coating, and also the anodized nickel phosphorus coating. From these two different images, we can see the nanotubes on the bottom images, and we do the electroplating into the nanotubes and get the anodized nickel phosphorus coating. This is and the surface of the zincated nickel phosphorus coating is different from the anodized nickel phosphorus coating. You can see the surface, the zincated one is very smooth, but the anodized nickel phosphorus coating, they have a nodular structure, which may cause different wear properties. For the micro hardness, they have, because they deposited the same coating, nickel phosphorus, so they have general same hardness for the zincated one and also the anodized one. But the advantages of the anodized one is obviously because they can see they have a better adhesion, coating adhesion. After do the bonding tests, you can see the anodized nickel phosphorus coating are still on the surface. It have a very good adhesion. For the wear mechanism, because they have a different surface structure, so the wear mechanism are different. We can see during the wear process, they have a different wear mechanism. So they have a different wear track. The wear track wise for the zincated nickel phosphorus coating are around 500 microns, but for the anodized one, they only have 133 microns. The corrosion resistance for the aluminum substrate and also the zincated one and anodized one are present in this image. We can see the anodized one have the best corrosion resistance. Another research for the electrode deposition based on the anodic oxidation one is the hydrophosphorus coatings. The first one we do the first nickel electrode deposition on the surface and get the nodular nickel layer. Then we do the second nickel electrode deposition and we get the needle nickel crystals. Then we do the organic modification and we get the self-assembled organic layers, and finally we get the hydrophosphorus coating. The surface morphology of our coatings with different electrode deposition times applied for the outside nickel coating are presented in the right image. We can see they have a different surface morphology. These are the contact angles results. You can see when we do the 10 minutes electrode deposition on the outside layer, we can get the best contact angles. Due to the wetting properties and due to the best wetting properties and the 10 minutes samples, they have the best corrosion resistance. Then I want to just introduce our research institute. I worked in the Jiangsu University of Science and Technology. This university is a key university of Jiangsu province. It's located in the east of China, East China. Yeah, it is an engineering-oriented university. And right now it's the top 15 evaluated by the Chinese Ministry of the Education. Our department. Yeah. Right now we have 115 staffs and also around 500 postgraduates. And this is our laboratory, and also we have the workshop, so we can do the research in the laboratory, and then we can apply our research outcome to the workshop, and we can do the pre-treatment line, we can do the production line, and finally we want to put our research outcomes into the real application. And also we have the research platform, a key lab of the Zhenjiang City, and also the Engineering Research Center of Jiangsu Province. Finally, I want to just want to finish the task. This is for the introduction of the Journal of Central South University. As an editor, I hope you guys submit your paper to these journals. This is a very good journals. Right now, it is level T1 in the science and technology journals. Another journal is that the Transactions of Non-Ferrous Metals Society of China. Hope you guys can submit the best results to this journal. This is a very good journal. Right now, it is in the GCRQ1 and have high impact factors. Thank you for your attention.
Thank you very much, Professor Yongxin Wang, for sharing a great knowledge with us. It is really our pleasure to welcome you in this virtual conference. So, and thank you very much for timely completion of your presentation as well. So we have a couple of minutes so that we can have some questions from the participants. So do we have any questions from the participants? I think
if I may ask, Dr. Shakur, I had a question regarding the mechanical properties and how it has been correlating with the.
Yeah, you can ask. Yeah, no worries.
Yeah. So I wanted to ask about the mechanical properties of these composite films and how they are correlating with the particles and the density of the particles. Probably, I don't know, either you didn't show or I missed if there was any information regarding them in the presentation.
Well, thanks for your questions. Because when we do the coatings, we're using the electrode deposition method. For the general method is that we directly add the nanoparticles of nanotubes into the electrolyte, so we can get the nanocomposite coating. But we use the soul to do the enhanced coatings. To our knowledge is that the better dispersion of the nanoparticles, the better properties of the coatings. So when we do the soul enhanced method, we can get a very good dispersion, very good nanoparticle dispersion. So we can get a we can achieve the improvement of the mechanical properties and also the corrosion resistance. That is the reason. Yeah.
This is clear, but have you measured the mechanical properties like doing nano indentation, any mechanical testing on the coating to see how it improves and compare, and also correlate that with the concentration of the nanoparticles in the coating?
It depends on the coatings. When we do the gold coatings, usually the coating thickness is very thin, so we use the nano indentations. But when we do the nickel coatings, we usually electrodeposited for a very thick coating. So we can do the mechanical properties by using the micro hardness tester.
Thank you. Thank you.
Thank you very much, Professor Yongxin Wang, once again for nice presentation and joining us this virtual conference. Thank you very much.
Thank you for your help. Yeah.
So now we move on to our next speaker. Our next speaker is Dr. Mariana from University of Lisbon. Let me introduce Dr. Mariana. Dr. Mariana studied at Belarusian State University from 2003 to 2008, Belarus, and later she obtained her PhD degree from Instituto Superior Técnico, University of Lisbon in 2016. Presently, she is a postdoctoral researcher in the group of Professor Fatima Montemor at IST Lisbon, Portugal. Her research is concentrated around the localized measurements, electrochemical and others, applicable to different scientific fields of study, including corrosion, biomaterials, fundamental research, and since recently, energy storage. Specialized in micropotentiometric studies employing ion selective microelectrodes and including their developments. Advanced multi-sensor experimental setup for localized quasi-simultaneous data acquisition, pH, NO2, current density, etc. Dr. Mariana is co-authored of 45 papers in international peer-reviewed journals and one book chapter. She conducted several trainings and application of localized scanning, vibrating electrode technique, and micropotentiometry to corrosion studies at academic and industrial facilities around the world. Today, she is going to talk about localized sweat studies for corrosion application and their enhancement. Please welcome Dr. Mariana.
Hi, can you hear me? Can you hear me well?
Yes, we can hear you very well.
So I'll share my screen. My screen. Let's go to. Oh, yeah. Entire screen. Yes. Okay. I'm going to my presentation. Can you see now the presentation side?
Yes, we can see.
Can you see it? Okay. So thank you so much for introduction. I really will be talking to you regarding SVET. And SVET is scanning vibrating electrode technique. Is a localized technique which is often applied to corrosion studies. So I also will introduce the technique by itself and its possible enhancements. So what is the work stage? Just to give a brief introduction, we get the camera, which provides very high magnification. We get the motorized stage, which allows digital movement of the vibrating probe or microsensors at microscale precision, like 0.8 micrometers. We have the holder for our specimen, for our sample, and then we have, in case of SVET, we have vibrator linkage, which holds this kind of needle-like tool, which is our SVET microsensor, and it vibrates in horizontal and vertical directions. And usually we use only a vertical component of this vibration. Yeah. So SVET is a microscale technique, and it also can be complemented by other microscale techniques, such as, for example, micropotentiometry, with the tip size usually even smaller than SVET, or dissolved oxygen microsensors. So SVET provides us information on current density. Micropotentiometry provides us information on distribution of the particular species. For example, a pH or sodium or chloride, and then dissolved oxygen naturally provides us, fiber optic sensor provides information on the dissolved oxygen concentration. So why these parameters are important? When we know the distribution of current density, we are actually able to identify the location of anodic and cathodic activity. And then if we complement our current density distribution with pH distribution, we can correlate the values of pH to distribution of anodic and cathodic activity and also distribution of the corrosion products. In some cases, the most complicated cases, dissolved oxygen microsensor is very helpful and handy because it helps us to characterize better the cathodic reaction, and sometimes it is tricky. Of course, we can go and enhance this approach even more, studying some other species. So all these techniques can be applied either in a single mode, or they can be coupled or tripled. Yeah. So if we talk about SVET, we can use it with all the other combination with other techniques. And why is it important? Why exactly why we invest in localized corrosion studies? When we have a corroding surface in electrolyte, there is actually a difference between the processes which occur near the surface at the microscale distance and bulk solution. And such techniques as electrochemical impedance or cyclic voltammetry, they actually give us the average response from the surface or the response from the bulk solution without providing the information on the individual species involved in the process. And localized techniques, as I mentioned before, micropotentiometry, SVET, or detection of dissolved oxygen, they actually provide this unique information of what happens right near the surface at microscale distance. And these techniques can be applied to a wide number of substrates. For example, it can be self-healing studies. It can be studies of inhibition processes. It can be studies of cut edges. It can be study of intermetallic structure or grain boundaries and precipitation, and many more. So when we study the process at microscale, and when we understand their mechanism, we have better chances to tailor material properties and reach sustainability eventually. Yeah. So typically, how do we perform our studies? There are two typical sample configuration: embedded samples, traditional for cut edge, for example, or some models, or coated samples, when we take a small piece and it can be studied either intact or with a defect of different shape. Can be point, can be scratch, can be something different. Then we place it or fix it on the top of holder and leave exposed only the part of the surface that will be measured during our localized study. And traditionally, we use three approaches. Yeah, we can divide everything in three approaches. Either we take reference sample and several modified samples, or we take one sample, and this one sample may include inside several zones which could possess different behavior, or we work with the model sample and we study that model sample under different conditions. In all the mentioned cases, what we are looking for is the difference. And then knowing the difference, we are looking for explanation of the difference that we could find. So now we'll take a look at some recent key studies, and I'll try to frame them in more applicability to oil and gas industry. So in the first case, it's directly the case of steel study aimed for application in pipelines, oil and gas industry, and we used polyolefin coating. Our task was to improve the coating by introducing the particles loaded with inhibitor. Yeah? And in our case, we decided to introduce hydroxyapatite particles loaded with cerium. And as I said before, this is a typical approach. We take reference and take modified sample. So the reference coating, we studied with scratch, and we could see activity in pH and in current density distributions from the beginning of immersion until the end. And we can also see that the activity was growing. In contrast, when we take a look at the modified coating, we see that no activity was detected neither by sweat nor by pH microsensor. But we also notice a remarkable healing effect because the scratch almost disappears. And we decided to study additionally how this healing happens. Right now we can see that the scratch is literally healing in front of our eyes. However, we cannot recognize using pH and sweat microsensor at this moment what was the reason, what targeted the healing, because there is no activity, and maybe the inhibition is so efficient that it happens before the species are able to reach our microsensors. So in order to understand if there is any effect of pH, we set up a different experiment, and we decided to study our coating without a substrate, only with the scratch in solutions with different pH. And this is what we can see in this slide. Yeah, there is no substrate, and we studied in acidic pH, neutral, and alkaline. And as you see, healing actually happens, and either acidic or alkaline pH, both, they assist healing process. To study it additionally, we made, of course, physical chemical assessment of the scratched area of the coating, inside scratch, outside, before immersion, after immersion. And we could actually see that after immersion, there are whiskers or kind of like recovering of the polymer structure inside the scratch. Yeah, we can see it in several images. And we applied micro-Raman, we applied micro-FTIR, and we were able to identify the mechanism of the occurrence. We know that our coating has primary amine groups inside, and we also know, and it was this information was provided by producers, that it has some carboxylic groups. So under conditions that are created during corrosion process, there is a possibility that in presence of cerium ions, there is a transformation similar to Hofmann rearrangement, which results in production of the polyurethane bonds, which literally recover the polymer chain. So this is what is responsible for the healing effect. And on the other hand, we have release of cerium and phosphate ions. And cerium ions help us to block the cathodic process, inhibit the cathodic process. And phosphate ions coming from hydroxyapatite, they help with inhibition of anodic process. These results are also published. Yeah. Now we'll take a look at aluminum alloy. And our idea was to study two types of polyurethane coatings which contain zinc. And we needed to understand either if there is any self-healing or corrosion inhibition present. We were able to identify healing inhibition in all kinds of, in all the coating that we tested. However, they were too good. And what we could see that zinc is being dissolved, but it was difficult to understand which of them is actually better. So we decided to study a modeling sample when we take a rod of the same type of alloy, embedded in epoxy, and we study it without inhibitor and the same electrolyte, but with different quantities of inhibitor, which correspond to different amount of zinc released from two types of coating. And as I was saying before, we can really see the difference. And the coating which provides higher amount of zinc ions actually is able to provide better corrosion protection. Right here we talk about aluminum, but this approach would be the same way applicable to steel substrate. For example, we could embed a steel rod and study systems containing inhibitors efficient for steel. So now let's take a look at one more case, which is, again, we talk about the aluminum alloy, but right here it's one sample, but this one sample contains different zones because we talk about the friction stir welding. So there are three different zones, the same way that it could have happened in case of steel welded samples. And we had to study their behavior at localized scale. And what we could see that thermomechanically affected zone and heat affected zone were actually the ones the most susceptible to corrosion and showed the highest corrosion activity. And on the other hand, we also can conclude that the influence of the welding process on corrosion resistance of the nugget and on the base material was actually negligible. Yeah. And so this was important conclusion here. Now let's take a look at one more case, and that will be aluminum alloy. And we study 3 different types of conversion coating and compare how they could improve the corrosion protection. So we first made standard approach, and when we see so many colorful distributions, it becomes more difficult to analyze them. And also, as the conversion coating introduces nanoscale modification at the surface, comparison becomes even more complicated. So in this case, the enhancement of the approach would be not just to make sweat measurements, but also approach to data analysis. And to analyze this huge amount of data, we can, the simplest approach is to compare the maximum and minimum absolute values of current density. Or more advanced approach would be to compare the integral values. When we take positive, negative, we integrate the values, and then we normalize them by the area size. So this kind of plot can be built, which actually allows us to make better and more reasonable analysis of the obtained results. So we can see that at treatment number 3, the one which is violet color, it was able to reduce anodic and cathodic activity both. On the other hand, if we take a look on absolute values, we also can make the same conclusion in this case. However, if we take a look on the integral plot, there is one more conclusion that we can make. If we take a look at the bottom part, the one which is cathodic, the green line is the one corresponding to the bare aluminum substrate. And we can see that actually all 3 types of treatment were able to reduce cathodic current density. And this conclusion is actually, it was not possible to make if we would take a look at the plot with absolute maximum and minimum current densities. This is just the case to emphasize the importance of the approach to data treatment when we get huge amount of results. So now we'll take a look at the beautiful case when we studied magnesium alloy and we studied smart corrosion inhibition. And in our localized study, we were able to reveal the pH responsive cyclic activation of corrosion inhibitor. So as I said, it was magnesium alloy Z31. And we had a coating, Zol gel, which was modified with cerium organophosphate. And traditional assessment was to take our substrate, make a defect, and we tried several times to make sweat measurements. And in this case, the enhancement of use of the sweat was addition of another sensor. So we use pH microsensor. And everything looks quite expectable for magnesium substrate. However, after we made long time measurements for about 5 days, we noticed that there is a cyclic reproducible activation and inhibition observed for our samples. We repeated tests several times, and actually even the timing of inhibition was very reproducible. So what we can see is that when pH increases and when we have the increase of corrosion activity, then it follows by drop of that activity. And we, using our additional studies, also physicochemical assessment, we're able to identify what happens. So when pH increases, this is our organophosphate. And with increased pH, we have excess of hydroxyl anions, which hydrolyze our organophosphate. So at high pH, when activity grows, pH is higher, and organophosphate is hydrolyzed, and the ions of serine and ions of organophosphate moiety are released. So inhibitor starts working. Then inhibitor makes its effect, so the corrosion process actually intensity decreases, and then the release of the inhibitor species also stops. And then as the cathodic and anodic process are not completely blocked, it starts developing again with some time. And again, when we have increase of pH, it targets the activation of inhibitor. And we were able to observe this effect several times during 5 days. So the activation is really cyclic. So actually, I hope that I was able to convince you that the localized techniques such as SVET in particular, applicable to a wide range of corroding substrates. Also, we can enhance the studies not just by our experimental setup, but also enhanced advanced data treatment, and addition of some other microsensors into setup. And I think it's really important for us to understand the mechanism, because understanding the mechanism would also help us to improve significantly the corrosion protection. At this point, I would like to acknowledge all of my colleagues and collaborators. Also, I would like to say thank you for inviting me to give this talk, and thank you for your attention.
Thank you very much, Dr. Mariana, for a very nice presentation. And really, personally, I like the presentation of the localized electrochemistry, because we are dealing with all such techniques. And hopefully my research members will also visit Lisbon next month, inshallah.
Yes. I hope so, yes.
So any question from the audience, please, because we have 3-4 minutes, who can entertain 2-3 questions. So any question?
So I'll take a question. So Mariana, excellent presentation. Like Dr. Shakur said, this is something that is close to what both of us do. So it's obviously exciting to see this approach and how it can help us build the scale understanding, right? So specifically talking about magnesium, can you talk a little bit more about what were some of the common challenges, and how small can you go when you're dealing with your samples to resolve the activities that you were showing just now?
Actually, we can go quite low, yeah. So as we talk about microscale studies, SVET by itself has microsensors about 12 to 18 micrometers. And if we use, for example, pH, we have microsensor with even smaller tip. If we have even smaller tip, it means around 2 microns. It means that we can go even more precise. I think we can resolve features of about guarantee 15 micrometers we can resolve. We can go even below 15 micrometers depending on setup. So I guess if there are some features with strong activity of about 5 microns, we still can try to work it. Also, sample preparation is important. The choice of solution is important, probably. Could be important to decrease the concentration in order to slow down the kinetic of the process, because you know that the huge problem with magnesium is bubbling, and hydrogen bubbling actually damages the sensors and may interfere with performance. So as long as we find a way how to control or predict or eliminate the effect of these bubbles, we can work. And the areas that we would be able to study could be around 200 microns per 200 microns, or 300 microns, 300 microns. Most probably we could go that low. Because traditionally, we study areas around, for example, 2 millimeters per 2 millimeters, or 1.5 per 3. in case of magnesium, especially if you would like to see intermetallics, we should go lower. And also, often we have to use techniques separately, not simultaneously. Because if we go really low, there is a difference between positioning of two probes. And in order not to lose information, it's better if we make studies separately. Yeah. So it takes it's more time consuming, but it would be possible to do.
Well, thank you so much. I think this is excellent, and of course, I have so many other questions regarding magnesium and the processing that you were showing. Hopefully, we'll get a chance to speak about those in the sidelines of this. But thank you so much, and Dr. Shakur, over to you again.
Thank you very much.
Thank you.
Once again, Dr. Mariana, it's really our pleasure to welcome you and, to have such a great knowledge from your side. So thank you very
Thank
much
you.
for joining us.
Thank you. I'll try to stop sharing. Yeah.
So now we can move to our next speaker, Dr. Afroz Barnosh from Kiri. Let me introduce our distinguished speaker. Dr. Barnosh is a principal scientist in the Croyan Center of the Qatar Energy and Environment Research Institute, which is commonly known as Kiri. At the same time, he holds an adjunct professorship at the Croyan Center of Curtin University in Australia. He received his undergraduate degree in extractive metallurgy of non-ferrous alloys in 1997, followed by an MSc in Croyan engineering in 1999. Both degrees were obtained from the Sharif University of Technology in Iran. After 4 years working in the industry as a consultant engineer in the corrosion and corrosion protection, he moved to Germany, where he received his PhD in 2018 from the Saarland University. The topic of his PhD thesis was hydrogen embrittlement revisited by in situ electrochemical nanoindentations. After 4 years of research and teaching experience at the Saarland University as a research group leader, he moved to the Norwegian University of Science and Technology, NTNU, where he worked as a professor of material science and engineering for 7 years. Dr. Barnosh is an internationally known expert in the fields of hydrogen embrittlement and nanomechanical testing. He is especially well known for developing multi-scale in situ techniques to understand the complex interaction between the microstructure, processing, properties, and the material's performance. He uses his understanding to describe the material performance in extreme conditions. He has 98 peer-reviewed publications and H-index of 22 on Scopus. His title of presentation is Understanding the Hydrogen Embrittlement by Multiscale Materials, Characterization and Testing. Please welcome Dr. Afroz Barnosh.
Unmute and start the video. So you can see my presentation, I hope.
Yes,
Everything is
it
there.
is
Okay,
really very
excellent.
good.
So thank you very much, Dr. Shakur and Dr. Bilal, both of you for giving me this chance to make the presentation, and thank you very much for a kind introduction. So as you said, I had the privilege and I was very lucky that Professor Michael from Texas A&M just made a very comprehensive and beautiful introduction to the hydrogen embrittlement. And just before me also, we see this multi-scale approach and localized approach to corrosion by the previous speaker. So it's make my job a little bit easier. And I can try to go to the main topic, which is hydrogen embrittlement. And as you may know, the hydrogen embrittlement is in fact happens when we have mechanical aspects, material aspects, and environmental aspects overlaying on each other, and at the center then we can have the hydrogen embrittlement. When we are doing the hydrogen embrittlement research, though, we have the challenge that regarding the different aspects in our experimental approach, we can control mechanical or environmental approach by different modes of testing, but material aspect is something which is dictated by the material itself. And then, as has been raised several times in the previous presentation, we are dealing with a multi-scale problem. So our modern view of material deals with the material from nanoscale, when we have atoms, crystals, defects, up to larger scale when we have interaction of the defects with each other, grain boundaries, then different grains interaction with each other, second phase, texture, then cracks, and the surface effects. So once you want to understand how material is behaving, then you have to consider its behavior at different length scales. But then, if you remember the previous image where I showed that overlapping of mechanics and environment with the material, then you can imagine if you have mechanics, then a stress can affect each one of these microstructural features in a different way, as well as hydrogen, which can interact with these different microstructural features differently, as it is schematically here shown. So we can have hydrogen as a solute atom in the lattice of the crystal, or we can have it as a void in the junction, or hydrogen at the dislocation cores, hydrogen vacancies, and then if you go further, hydrogen which is segregating at the grain boundaries or interfaces or cracks, crack tip. So hydrogen at different microstructural features can affect the properties differently. And today I'm gonna give you examples of this localized approach where we're trying to understand the effect of the hydrogen at these specific microstructural features by testing at the different length scales, and of course by focusing specifically at the lower scales and using techniques like nano indentation, micropillar compression, or cantilever bending tests, as you can see here. So because of the limitation in time, I will focus only on these two, so micropillar compression and cantilever bending. And we applied these methods, in fact, to the same alloy that Michael showed earlier today, alloy 725, specifically because this is a very promising alloy for the corrosion resistance in oil and gas. So if you have a corrosive condition in an oil and gas system or industry, and then you have a very critical component, you have to be sure that nothing happens to this, then typically you go for alloy 725. But with the time, we notice that this alloy suffers from hydrogen embrittlement, and this is important to look at the hydrogen embrittlement of this alloy. So this was an example of alloy 725 in a solution annealed condition. So I can again try to show you the picture. So we use a similar setup as Michael showed today earlier, a Camerat and Weiss in situ tensile machine. And this is a tensile sample that we are deforming inside a scanning electron microscope. And you see a very good ductility of this solution annealed 725 here. Then we take the same alloy and we charge it with hydrogen, 18 hours, and we reach to about 100 ppm of hydrogen in the alloy. And again, as you can see here, when we started to deform it, completely different behavior, a lot of crack formations, and the alloy failed after certain amount of the plasticity, as you can see here, with formation of a lot of cracks, and then one of these cracks grows to a final crack that you can see here. This is the stress strain curves of the alloy without hydrogen and the stress strain curve of the alloy after charging with the hydrogen. I have to say, we spent a lot of time on developing electrochemical techniques to charge the sample with the hydrogen, and at high temperature, about 80 degrees, so we can have a better hydrogen diffusivity and have a better distribution of the hydrogen in the alloy, and at the end also end up with a surface condition which is very good. So this is a sample which has been charged with hydrogen and then taken out of the electrolyte and tested, and you see the surface condition is still very good. What is important is formation of several secondary cracks. Most of these cracks we find out happening at the grain boundaries. So what we find out is that the grain boundaries in this alloy with hydrogen, after certain amount of the plasticity, start to fail. So the strategy that we take to study these grain boundaries was to isolate this grain boundary and look at them separately. So we did electron backscatter diffraction mapping, and in the map we started to choose a specific grain boundary. So with the map you can characterize the grain boundary. So we selected one of these grain boundaries here. It was a low angle grain boundary which supposed to have a good penetrability to deformation when you deform it. And then on this grain boundary we cut several micropillars with a focus ion beam, as you can see here. So this was the grain boundary and these are the pillars. So one of them magnified here. I need to use the, so this is the grain boundary and you see several pillars. One of the pillar and the grain boundary is exactly in the middle of the pillar. So this pillar was taken to the nano indenter, and with a flat punch, we just punch the pillar, and you can see the pillar after deformation. So to understand how the dislocations during deformation interacted with the grain boundary, we took this pillar to the focus ion beam again, and we cut a thin film out of the pillar in a way to have the grain boundary exactly here, grain boundary line exactly here at the center of this thin film. And this thin film was taken back again to the scanning electron microscope, where we did the so-called transmission electron backscatter diffraction. So the advantage of transmission electron backscatter is that it's not very sensitive to plastic deformation and you still get a very good Kikuchi patterns. So this was our deformed pillar, and you see the grain boundary. Here the inverse pole figure map where you see the two grains adjacent to each other and the grain boundary here. Image quality shows the transmission of the slip across the grain boundary. Also, kernel average misorientation shows that there is not a big pileup of dislocations behind the grain boundary, because grain boundary is a low angle grain boundary and slip was able to transfer to the adjacent grain easily. So this was the situation without hydrogen. A similar pillar with the same grain boundary and same orientation then was taken to our electrochemical cell, which is built to be put inside the nano indenter. So we have an electrochemical cell, our pillar is here, and the nano indenter tip is here. So we can charge the sample with the hydrogen in situ and then punch it with a nano indenter. So a same pillar was taken to the nano indenter, and here was the pillar without hydrogen, and this one was the pillar with the hydrogen. So we did exactly the same procedure. We took the deformed pillar with the hydrogen out of the nano indenter, went to the FIB, make a thin film, and then came and did transmission EBSD, and this is what you see. So exactly same pillar as above, this one without hydrogen, this one with hydrogen, and you see clear pile up of dislocations behind the grain boundary. So it seems when we have the hydrogen in the metal, the characteristics of the grain boundary is changing, and it's not as penetrable as it was before for the transformation of the strain and the stress to the adjacent grain. So the slip behind the grain boundary just stops, and it takes longer time to initiate the formation in the adjacent grain boundary. And this results in the formation of the cracks at the grain boundary. So that was the approach that we used to study the effect of the hydrogen in a solution anneal 725. But 725 most of the time is used in precipitation hardened condition. You see such an 725 precipitation hardened according to the API heat treatment here in this movie, where you can see that. I can show you the movie again. So you see, this is the 725 precipitation hardened. Again, relatively ductile. The fracture happens at 1.2 gigapascal. And the same alloy was taken to electrochemical cell, charged with hydrogen, about again 100 weight ppm hydrogen charged, and this is what happening to the charge sample. So you see extremely small amount of plasticity and very quick cracking of the material. You can see here the comparison of the stress strain curves. This was in solution annealed condition without hydrogen, with hydrogen, and this is in solution, in precipitation hardened condition without hydrogen. And then when we have hydrogen are these green and pink curve here. So we lose almost all ductility of the sample, and fracture happens very early. So in this condition, if we want to study the effect of the hydrogen at the grain boundaries, it's not as easy as before, and we can't use the pillar compression test. So here we are using a different approach. What we do, we are cutting cantilevers from the material where we can include one single grain boundary here, and then we can test this cantilever either in air without hydrogen or inside our electrochemical cell with hydrogen, and see what's happening to the sample when we are charging it with the hydrogen. So we did the experiment. Here is the bicrystalline cantilever free of hydrogen. See, very good ductility. The grain boundary is intact. Nothing happens to the grain boundary. You can see the difference in the slip lines in the root and in the cantilever, which shows that we are dealing with a bicrystalline cantilever. We use also this partial unloading to use fracture mechanics approach to measure the fracture toughness. Then a similar cantilever, just like this one, was taken to the electrochemical setup. We charge it with hydrogen, and that's what we observed. So in presence of the hydrogen, the grain boundary weakens so much that a crack happens here, and we have a very early fracture of the cantilever. So if you look at here, we deformed the previous cantilever without hydrogen up to 4 micrometer, while this one is only about 1 micrometer and start to form a crack and fracture happens. So it was also revealed that how sensitive are the grain boundaries in 725 to hydrogen, and hydrogen result in the decohesion of the grain boundaries. Now we are working on modeling the cantilevers using finite element analysis, incorporating both cohesive zone and crystal plasticity to use inverse solution methods and try to measure the cohesive energy of the grain boundary with hydrogen and how is it changing with the hydrogen in the material. So by this, I would like to summarize. I try to show you that hydrogen brittlement is a complex phenomena, requires looking at the material and hydrogen interaction at the different length scales. And as an example for the alloy 725, I try to show you that how hydrogen aggregation at the grain boundary changes the properties of the grain boundary, its interaction with the dislocation, as well as its cohesive strengths. So by this, I would like to thank you, and I would be happy if there is any question for me. Thank you very much.
Dr. Barnosh, for a great presentation. Questions from the participants? We have 5 minutes. We can entertain 2-3 questions.
Hi, Afruz. Can I ask you a question?
Yeah, sure, Michael.
Yeah,
That's
please.
great.
So, I wonder if you have the stress strain curves for the micropillar compression tests.
I do have it, but I'm not sure if I have it here. But the thing was that we did a displacement control indentation, and we tried to control the strain level of both pillars at the same level. So they have been punched to the same amount of the deformation. It's possible to look at here. Yeah, you see here, they all almost, no, unfortunately, I don't have the curves here. Yeah. But as you can see, I mean, the amount of I think we did like 10% or 20% of a strain for both of them.
Okay.
Of course, the load level was different. The one with the hydrogen required a little bit higher load levels, if I remember correctly, yeah.
And on the same point, Afruz, a quick question on the pillars compression. Did you guys sort of estimated what kind of rate that was when you were compressing this?
Okay, again, we are using the high citron system,
Right.
and we are trying to do several tests and set up the right PID, because sometimes you get instabilities and the system goes out of the control. So we try a lot to set up the best PID to control the displacement, to have a good displacement control. And then we are using like 1 nanometer per second, typically the displacement rate for most of the tests, yes.
I see, yeah, because in my experience, the typical challenge with the high citron is there's not much instrumentation there to actually see it. So were you just sort of pushing it down and hoping that it hits one of the pillars, or were you able to see the pillars?
I mean, yeah, I know exactly. I mean, if you try to do it load control, definitely it's not working, because you loading it and suddenly as the formation starts, then you don't have any more control on the things, and it's punched the pillar to the bottom and nothing remains. So it's very important to choose displacement control deformation, both for cantilever and pillars. And then again, as I said, it's extremely important to use right PIDs to control the displacement rate and have a the best possible displacement rate. So if you look at here also, I can show you in the cantilever. So you see here how instabilities starts to happen as soon as the crack formed in the cantilever. There are a lot of instabilities here. So.
Well, thank you, Afroz. I think there are a few questions in the chat window that we can certainly address as we go along. One last question, because that's important for me, because a lot of our students are working on the same topic. What was the electrolyte that you were using to charge these?
Okay, the electrolyte that we use for charging them, I mean, that's also another important. Just imagine this cantilever has been in electrolyte charge and is still so intact and good. Of course, nickel alloys are still easy and good. We did also test on iron-based alloys. They are terrible. We spend a lot of time to develop electrolytes to be able to have the surface intact during the cathodic charging. We are typically using a electrolyte based on glycerol and borate or boric acid. So this is for nickel alloy. Also, sometimes you are using glycerol and phosphoric acid if you want to charge it more. Get a better hydrogen charging. Yeah.
Well, thank you so much, Afroz. There is obviously a lot more interest in this talk because there are a lot of students and colleagues working in this area. We'll close it at this point, but we'll let the discussion flow on the sidelines of this. Thank you again. And you may want to check the chat. I think there are some questions there for you. Thank you.
Sure. Thank you very
Dr.
much.
Shakur, please go ahead.
Dr. Shakur, I think you're on mute.
Let's move to our next presenter, who is Engineer Manoj Abraham. He is Regional Manager, Hempel, UE. Let me introduce him. Engineer Manoj is a certified protective coating specialist with over 26 years of techno-commercial leadership within the paint and construction chemical industry in India and GCC. He is passionate about sharing his understanding of structural fire protection, corrosion science, and its prevention, acquired by practical experience and theoretical knowledge in coating and lining, covering corrosion protection, chemical resistance, passive fire protection, electrical insulation, etc. He loves to mentor, coach, and develop high-performing team in multicultural environment. He is very comfortable in presenting thoughts and ideas to small and large audience. He presented technical papers in various conferences. He has been acknowledged as a techno-commercial leader in the region with unique skills to bridge business needs and technology. He has worked with the coating engineers, specifiers, maintenance personnel in several oil and gas companies such as Saudi Aramco, Qatar Petroleum, Qatar Gas, ADNOC, etc. He is providing advice to structural engineers, steel fabricators, fire engineers, and design consultants in the civil infrastructure market. He's a civil engineer from Madras University and has done his MBA from SP Jain School of Management and currently a doctoral scholar pursuing research in the field of sustainability and business. He has spent more than 23 years of professional life in GCC and he is currently the regional manager for instrument coating in the Middle East for Hempel Paints. His title of today's presentation is Lessons Learned from a Major Fire Accident in the Middle East, a Structural Steel Perspective. Please welcome Dr. Manoj.
Thank you, Dr. Shakur. Kind of you. Let me share my screen. Let me know once you're able to see that. Are you able to see my screen?
Yeah, it's fine to us.
All right. Okay. Thank you so much for the.
Can you, Engineer Manoj, can you go to the presentation slide?
I think I can.
Yeah, here, yes.
Yeah. Can you see it
Yeah,
now?
it's fine. It's fine
All
now.
right. Okay. Thank you very much for the kind words. Really appreciate the opportunity that I got in an August audience. Right. I'm more from the application side of it, not so much on the research side. But I would like to share a few examples of how we can protect structural steel at the time of fire. Right. So the agenda goes like this: what happens when there is fire? When there is a fire accident, what is the structural perspective and what happens? What is intumescent coatings and how do they work? And a few examples of projects. Again, I've looked at Qatar specifically because I've worked there as well, and this presentation is also there. Right? Okay. This is one of the restaurant owners in Portugal who basically said that intumescent coatings saved his restaurant. So let's try and identify what and how an intumescent coating works. This applies both to oil and gas and civil infrastructure applications. The examples today that we will show is more civil infrastructure. Now, these pictures are primarily from my work and the work related experience that I've gained. This was a medicine warehouse in Salva industrial area, which got burnt. And as you can see, a typical fire affected building collapses internally, right? The main columns buckle under the load and they are not able to take the required load due to the effect of fire, and they collapse internally. And when they collapse internally, what basically happens is it traps people. So it leads to injuries and sometimes even fatalities because people are not able to escape because the structure collapses inside. The next slide shows picture of one of the biggest malls in Qatar, where there was a major fire accident. But you can see that the structure has not collapsed, but it is very, very stable. And this made sure that there was no injuries or fatalities. So what you basically see here is the steel beams, both longitudinal and transverse, are intact. You can see that the glass is shattered, aluminum is melted, but the structure is intact. In fact, additional testings were done to identify if there is any change in the crystalline structure of the steel, but there was no problem. And you can see that there is a carbonaceous char that is formed on the steel structure. A close-up I would show here. You can see that this is me, measuring the depth of the char that has formed, where basically what has happened is that the coating that was applied, which was called intumescent coating. To intumesce means to swell. The coating swells and forms a carbonaceous char, which is an insulating char, and it prevents additional heat from going in to the steel, wherein the steel gets weakened. All right. So this is something that we learned from a project that was live, and I was able to go and investigate and check the coating that was applied and how it was performing. So you can see that a close-up shot of one of the applications, you can see the primer still intact, and you can see that the top coat, and in this picture, I think it is even more clear. You can see the top coat has burnt off, and then the intumescent, which is this white color, is being consumed based on the increase in temperature. More and more char is being formed. So this is a close-up shot that you could see. So what we basically know is that steel loses temperature very, very quickly as loses strength very, very quickly as the temperature increases. So when it is about 558, it has only 60% load carrying capacity. At 630, only 40% load carrying capacity, and at 20% and only 20% at 725 degrees centigrade. So basically what happens is that as the strength is lost, the structure starts to collapse. Now look at this. There are two types of fire that normally happens. One is a cellulosic fire. So when you look at a shopping mall, your warehouses, your hospitals, what burns are wood, textiles, paper, cotton, right, things like that, which is basically plant based. So they are called cellulosic fire. The other fire is called hydrocarbon fire, which you will see in petrochemical plants or offshore facilities, where it can be either a jet fire or a pool fire. Pool fire is when you have a tank, a diesel tank, it burns until all the fuel is complete. But a jet fire is when there is a pressurized source of fuel coming through. And the orange curve is the hydrocarbon curve. This is the cellulosic fire curve. And you can see that within 20 minutes, right, the cellulosic fire reaches more than 700 degrees centigrade, but a hydrocarbon fire in less than 2 minutes, it already crosses 800. And we know, as we discussed earlier, that the time taken, right, for the temperature to reach only 20% load carrying capacity is 700. And you can see that this unprotected steel crosses 700 degrees centigrade. So here the steel has only 20% load carrying capacity. So what happens is that the structure collapses. So there is no time. So people are not able to escape within that time. That leads to injuries and fatalities. So what we try to do with our intumescent coating is that we are ensuring that the steel reaches not more than 630 degrees centigrade, where you will have at least 40% load carrying capacity, thereby making sure the structure is stable and people are able to come out, right? That is a primary role that we do. So we are part of what is called as a passive fire protection. Active fire protection is provided by sprinklers and the fire engines which come in. So there are several types. You basically have uh, reactive and non-reactive types of systems, and you can see that an intumescent coating looks very much like a paint. So now more and more structures are with exposed steel. You go to any airport, you will see the steel exposed. Even shopping malls, you will see that the steel is exposed. That is how. And when the steel is exposed, you want a coating which looks nice, pleasing, and at the same time you also want it to make sure that there is no corrosion, right? So that is an issue as well. So we want to ensure that there is no corrosion coming through, right? So let us look at how this works, right? I want to share this video if it plays. All right, so generally what happens is the coating expands. The coating will expand, and thereby it will ensure that the insulation happens. I don't know why this is not playing. All right, okay. So what basically happens is that you have this steel panel and you have the fire coming directly impinging on this coating here, right? And what will happen is that as the temperature increases, the coating will expand and it will form a char, which then will make sure that this char is an insulating char and it will prevent this heat from reaching the metal substrate below. Yeah, so that's what happens. So what will happen is that this coating, the intumescent coating, uh, will ensure that heat does not transmit from the fire onto the coating, because of which you will get structural stability. All right, okay. So in general, what happens, I think a little bit of understanding. There is a phosphate breakdown. What primarily happens is you have a resin, a binder system, where you will have a carbon source. You will also have a trigger mechanism where there is a catalyst which triggers that once the steel reaches about 200 degrees centigrade, there is a breakdown. One of the primary constituents of this is a material called ammonium polyphosphate. So it starts to break down and it reacts, and there is an esterification of the alcohol. And then as the temperature increases, the carbon starts to evolve, and there is a foaming agent which pushes the intumescent up. Let me show that in a little detail, right? So what you basically have is that the ammonium polyphosphate, as the temperature reaches about 200 degrees centigrade, breaks down to form ammonia and phosphoric acid. And this phosphoric acid combines with one of the carbon source, and it forms a ester. Okay, it's like a phosphoric ester. And as the temperature increases further to about 280 to 350 degrees centigrade, this ester breaks down, giving out carbon. There is some water released, and there is acid such as phosphoric acid released as well. At the same time, when this is happening at around the 280 to 350 degrees centigrade, you have materials which will release gases, right? So commonly we use materials like melamine or chlorinated paraffin. What they do is melamine releases a lot of nitrogen. You have chlorinated paraffin giving out a lot of hydrogen chloride, which is shown in the equation here. And what happens is that these gases, which are not non-flammable gases, will evolve, and so you have the carbon coming out. There is a gas evolving, and the binder, which is typically acrylic binder, which is used in a cellulosic fire. If it is an epoxy fire, you might use an epoxy binder, and these binders melt and form a layer which will prevent the gases from going out. So what happens is that the char increases. It's unfortunate I'm not able to share the video for you. It would have shown very clearly. So what happens is the char increases, and you can see that the coating thickness, which for example applied at 1 mm, would reach about 50 mm in its thickness, and it increases, and it forms a char, a carbonaceous char, which prevents heat from going in. It will be an insulating char, and thereby the steel structure is protected. Yeah, so that's so primarily what you will have is structures like this. You have I beams, you have hollow sections, you have it might have concrete on top like this beam. You can have hollow sections with concrete filled. So all these structures primarily used in construction industries will be protected with an intumescent coating applied like this. But what is also important is to ensure that you apply it correctly, right? So based on the environment, uh, as per ISO 12944, we divide the environments in the corrosivity category. So if this is the lowest corrosivity category, C1, you need to apply a primer and a top coat. But if you look at a C3 interior, you might need to have a polyurethane top coat, right? But if it is in a C4 environment, coastal, then we would need to have like a zinc rich primer, epoxy primer. You can have a solvent based intumescent coating and a polyurethane top coat. Just a few things that we need to check. We need to ensure that the environment that the product is used is the right one. You can see these are typical examples. This is again another shopping mall in Qatar, in Doha, where you can see that a wrong choice of the intumescent coating has led to premature failure, right? So this is in a semi-exposed environment. So with high humidity that we see in Doha, this is not internal. This steel that you see here is not internal, right? So a water-based intumescent was used and it has failed, right? This is a close-up shot, and what you can see is literally brittlement. Brittle. The coating has absorbed moisture and it's become very, very brittle, right? So remember that not all coatings are equal. what we need to look at is the correct product to be used at the correct for the correct environment. And what we need to ensure is that the products are tested, say for example to a European assessment document, or there is a European standard called 16623, and we apply the correct primer and the correct top coat to ensure that we have the right product used. I think that's very important. These test standards will give you guidance from a durability perspective to see which product can be used where. There are several standards. The best is products tested to X category. They should have passed, which means that it can be used in a C4 environment. And we know that we have had several accidents. I don't want to name, but it is important that the suppliers, the architects, the designers, the consultants have a big part to play in the value chain. So that's very, very important that we need to do that. Just a few examples. You will see this on the F Ring Road. G Ring Road. You will find this where a coating was applied. This is near our Doha airport. You will see this is being refurbished. You will see that this is the Palestinian Sudanese school. So just a few things I wanted to share to you about our intumescent coatings and how they will work. So I can answer some questions. I think I saw one where people are talking about the cementitious coating. I think a cementitious coating is important. It can be used as well, but it doesn't look nice. Number one, aesthetically, it is not very pleasing. Second, you have corrosion between the cementitious material and the steel substrate. So that is a problem. And yes, the next question was about thickness of the coating. Very, very true. We calculate the massivity of the steel, and based on the massivity, then we can get the correct thickness that is to be done. And these are all third-party tested, and we have test reports done. There was another question. I could not pick it up. Is there any other? There are a few more questions.
So please, if anybody has some question, he is admitted to ask, please. So if not, I have one comment, Engineer Manoj.
Yes.
To be very honest, the one of the objective of this conference was to bridge up the gap between the academia and the industry.
Okay.
So because today's presentation really it is very nice and very informative. So whether there are some possibilities if you can have some collaborative work between TAMUQ, Qatar University, and the HAMPEL. Whether there are some possibilities are there?
Yes, very much. In fact, I know we are currently doing some tests in Kiri, where some of our products are being tested. I've always been quite active. So there are things we do as HEMPEL. We work with academia to basically do like a third-party testing for verification, right? And also what we do is, if there are opportunities, I'll be more than happy to share some of the ideas. Even your students, can probably do some research, right? There's a lot of work we can definitely do.
Like Qatar Shell and Q Code, Qatar Steel, and many industries in Qatar, they are collaborating with the institutes and they are having some collaborative research work. So I am asking about these lines. If possible, we can communicate, and Professor Bilal and other colleagues from TAMUQ and Qatar University, they can approach you and we can have some, the mutual field of interest in future.
Definitely. As I told you, we are currently doing some tests in Kiri as HEMPEL. We have some of our products being tested in Qatar. So that's something that we will continue to do, and we will be happy to collaborate.
Okay, Dr. Bilal, do you have any question from Engineer Manoj?
No, thank you so much, Manoj. It was a very revealing presentation on where your organization is and how we may be able to get in touch and collaborate more. So we appreciate that, and it's good to know that you're already working with Thierry. And one of the purposes of this conference in the past has always been to connect industry with academia. So inshallah, we'll get in touch, and we'll have a lot more to talk about data. Thank you.
We'll be happy to. Thank you so
Thank
much.
you very much, Engineer Manoj. It is really very interesting and very fascinating, the presentation. We learned a lot from your, the information. Thank you very much for being with us
Thank you.
today.
Thank you so much.
Thank you very much.
Thank you. Thanks for the time and the opportunity.
So we can now move to our next speaker, Miss, rather than Dr. Abhita Ramesh. Sorry for, because she is well known to us and we are very quite familiar to each other, So Dr. Abhita is working in QSA RTC. So let me introduce Dr. Abhita. Dr. Abhita Ramesh is a corrosion researcher at Qatar Shell Research and Technology Center. In her current role, she is responsible for management of over 24 R&D projects and asset integrity investigation laboratory. Dr. Abhita obtained her PhD from Indian Institute of Science, India in Sustainable New Energies and Bachelor's in Environmental Engineering. Dr. Abhita's research interests are focused in bridging the gap between the fundamental corrosion studies and the practical engineering solutions. She is particularly interested in understanding of the complex corrosion morphologies and the development of improved methods for prediction of long-term corrosion rates in real service environments and corrosion-related failure investigation. One of her key strengths is in taking an R&D project through the technology maturation cycle, where she specializes in taking a project and the outcome from the inception all the way to field deployment. She will discuss today about materials and corrosion R&D at Qatar Shell and overview. Welcome, Dr. Abhita.
Thanks a lot, Dr. Shakur. Yes, as you said, we've gone a long way, right? So I'm very glad. Thank you so much for inviting me here, and I'm so excited to share with you how we manage the R&D at QSRTC, and I think that also gives you an opportunity for everybody else to know what we do and how we come up with these projects here. So all the 24 projects that we talk about. So I'm just trying to share my screen. Please let me know when you can see it. Okay, I think you can see my screen right now.
Yes, we can see.
Okay, perfect.
Dr. Abhita, can you go to the presentation mode?
I'm trying to get into the slideshow mode. Yeah, all right, great.
Okay.
So as Dr. Shakur said, I'm Abhita Ramesh and I'm working at Qatar Shell Research and Technology Center. Without any further delay, I would like to start with giving you an outline of the talk today. So first, I will tell you a little bit about what are the different R&D projects, so what are the different themes that we work on, and then I pick an example from the pipeline integrity related projects to tell you how the project emerged, and so that will give you a flavor of what we do here in QSRTC. So in QSRTC, with the lab, so it started again with technical services. So we have the world's largest gas to liquid plant here in Qatar, and this gas to liquid plant, like any other plant, we have like any other asset, has some amount of challenges in terms of asset integrity, corrosion. So when these investigations come in and we start providing these technical services, that's when those get translated into R&D projects. I'll give you an example and explain how that works. And eventually, one of my specialization is translating this R&D project into a field deployable product, or patents, or in terms of understanding that can go and into a direct application into the site for obvious reasons. So if you see about 24 R&D projects, you see 22 of them listed in here, out of which about 14 of them are still ongoing. So far, we have completed about 6 field deployments, and 3 of them have been offshore. So the offshore project was with Dr. Shakur, where we were trying to test some surface tolerant coatings and comparing them with self-healing coatings that were actually produced in his lab by his team. And similarly, we have deployed about 5 corrosion coupons, and I'll tell you a little bit more about what that is. So far, we've had 2 patents, 42 technical communications in the form of journal papers, mostly, and few conference proceedings and invited talk. The value that we have delivered is about 9.1 million USD, out of which 2.4 million came from Shell alone. So we also sometimes co-fund some of these projects, and also write our own proposals and be LPIs in some of them, especially in the QNRF based projects, etc. So far, I've been working with about 9 universities and 4 industries in Qatar and outside of Qatar as well, and a lot of collaborators in-house and outside. So you can see a few collaborators that have been listed out here. We have multiple projects with Texas A&M, Qatar University. So we always tend to have a local partner, and we use the fantastic capability that we have in Qatar, and then collaborate with the other universities, such as Imperial College, University of Toronto, and Indian Institute of Science, etc. So this is how we work. So giving you an example of how the pipeline related projects emerged. So if you look at this is a pipeline from at Pearl. So we have 2 pipelines, Pearl 1 and Pearl 2, coming off from the offshore platform all the way to our asset. And the first unit where the pipeline comes onshore is into this unit called a slug catcher. So in the slug catcher, we have these corrosion monitoring coupons. These coupons are retrieved once every 6 months to study the integrity of the pipeline, to know what is the corrosion rate in the pipeline. So we take them out, do some measurements, and that's how we track the health of the pipeline in a way. The gas that we produce here and in the North Field is sour in nature, which means it has both H2S and CO2. So in an unmitigated situation, as you can see here, you have oil and condensate and water, and the water starts to condense on top because many of this is in the gas form when it is coming onto the platform. So when this starts to condense there, then that's where this region is prone to corrosion. And in a mitigated scenario, you would see, that we have the corrosion inhibitor in place. This inhibitor then compensates, it just stays on the surface, prevents it from any further corrosion. And also this region where the water comes in contact with the pipeline, the inhibitor tends to form a surface where it adheres to the surface of the pipeline and prevents it from corrosion. So that's why corrosion inhibitors play a very, very important role for us in protecting our pipelines. There are various other challenges that a pipeline brings forward, for example, stress corrosion cracking, and this is avoided by material selection and by making sure we have good quality control. Oxygen and elemental sulfur, but we don't expect to see this challenge in our pipeline anyway. And also in terms of preferential weld corrosion, and then under deposit corrosion in the pipeline. So these are some of the challenges that any pipeline would pose to an oil and gas industry. Today in our talk, I'm going to pick up the corrosion inhibitor bit and tell you how we are addressing the corrosion inhibition challenge, and also couple a little bit with the under deposit corrosion in the pipeline. So corrosion inhibitor, it comes with, so the corrosion inhibitor that goes into any pipeline has to go through a very long qualification process. And these methods are usually very cumbersome. I'll tell you why in a bit. We have 2 kinds of inhibitors, batch inhibition and continuous inhibition. And also we try to understand what would happen in the presence of, let's say, various kinds of deposit in our qualification procedure. Various other challenges that I've listed out are usually ruled out based on prior experience. We know how to manage them. And under deposit corrosion in the other operators in the Qatar North Field seem to have had some problems, especially in the slug catcher region. And Pearl's inspection so far has revealed no problems. But at the same time, we want to be ahead and then be quite proactive in our approach. And that's why this project was built. So how do these inhibitors basically work? So I did tell you about how the inhibitor forms a protective layer. So let's get a little bit deeper and understand the inhibition chemistry. So in the pipeline, if you can imagine, this is water, these are the condensates, this is gas with CO2, organic acid, and H2S. The water then starts to condense on the top. This is called condensation water. And when you look at it a little bit more closely, especially in the presence of inhibitor, the inhibitor has some amount of inhibitor gets into the oil phase. That's why CO is the inhibitor's concentration in the hydrocarbon phase, and CW is the concentration of inhibitor in the water phase. That is CW here. The inhibitor also tends to arrange themselves in form of micelles between the hydrocarbon and the water, as you can see, and some CI is also absorbed onto the pipe wall to prevent corrosion in here, like I just told you in the previous slide. So what are the different parameters that come into picture with respect to inhibitor qualification? So inhibitor partitioning coefficient, that is, this is the ratio of concentration of inhibitor in the water phase versus the oil phase or the hydrocarbon phase. This is a very, very important parameter for us. Other than that, we're also interested in dissociation constants. That you see that is KD that is derived out of the concentration of positive and the negative ions, cations and anions, how they disperse themselves, and also absorption of corrosion inhibitor, and this is governed by Langmuir's isotherm. Again, what we now do, so the dosage that is optimized for the pipeline is usually dependent mostly on the partitioning coefficient, that is POW. And this is of important to us. And so all the qualification studies, they look into this bit primarily. So this is what we estimate in our inhibition study. If you look at so the sour service pipelines, so Pearl pipeline falls in this region. So this is a sour region where you can have a significant amount of H2S. And so in Pearl pipeline, we have about 2.32 mole% of CO2 and 0.79 mole% of H2S. And Pearl GTL, if you see the CO2, partial pressure of CO2 versus H2S is less than 20, which means this is sour in nature, and where H2S concentration is dominant. And so the advantage of sour service pipeline is that, it forms a uniform iron sulfide layer, which acts as a protective coating. So in a way, I would say when we compare sour and the sweet pipelines, sour pipelines are relatively easier to manage. So what are the different acceptance criteria for corrosion inhibitor qualification? So primarily the inhibitor, the corrosion rate in the pipeline has to be below 0.1 mm per year. This is a very, very important criteria for us. There should be no pitting, and in all operating conditions, the inhibitor has to be performing pretty well. So what are the so you can see a bunch of primary and the secondary requirements that are listed here. Primary requirements are basically looking at what happens in the high or low TDS brine, in let's see blood temperature. So there are many other parameters that are important to us, and few other secondary parameters or acceptance criteria that we take into consideration is to make sure that it doesn't, let's say, kind of foam, and then that it has to have low emulsification, and then also it should not degrade in the pipeline after we inject this. So these are some of the secondary requirements that we see here. And also a very important criteria is CI is to KHI. So KHI or MEG is basically kinetic hydrate inhibitor. So the hydrate inhibitor, the main role of hydrate inhibitor, as it clearly says, is especially in the colder regions, when the temperature of the pipeline falls below 21 degrees C, that's when we start injecting KHI or MEG, and it prevents the formation of hydrates in the pipeline. But when we qualify the inhibitors, most of the inhibitors, they tend to actually perform have an increased corrosion rate and perform not very good in presence of this KHI or MEG. As you can see here, without KHI, the corrosion rate in mm per year is very, very low for a particular inhibitor. But as soon as we put MEG in, the corrosion rate shoots up. And this is a very, very important parameter. So imagine during winter when we have MEG or KHI in the pipeline, the inhibitors functioning could be hampered. So that's why we always make sure that our inhibitors are compatible with them, and that's why this forms a very important criteria in our inhibitor qualification studies. So we saw how we qualify inhibitors, what are the different parameters that we take in. So what are the challenges, and why are we so much concerned? If it's just a qualification, it should be very easy, right? So let me tell you what challenges we face there. So first is the duration and the testing conditions. So you see, here are a bunch of different test conditions that we have to literally follow and capture while we're doing this test. And every single, let's say, every single kind of every single condition that is listed here, for example, summer, winter, high TDS, low TDS, etc., each condition takes about 500 hours of testing, which is 22 days minimum, for every condition. So imagine if we started qualifying these inhibitors using the conventional weight loss method, then for these 8 different conditions, we're going to take months to literally qualify every single inhibitor. And this is just basic parameters. And then comes the advanced parameters, like in the presence of MEG, in the absence of MEG, etc. So this is extremely time consuming and very, very expensive. Also, the inhibition studies, in this 500 hour, we can only reproduce a tiny bit of pitting, so we cannot really see what would happen in terms of pit development in the presence of deposit, for instance, and how can we optimize the dosage. No, this cannot be done because it's in the 500 hours, it's simply impossible for us to see those kind of pitting. As a result, we need a very fast and reliable technique that can also take in the pitting assessment into consideration. And lastly, most of the pipeline studies are based on looking at the presence of sand and how the presence of sand really has an impact on the under deposit corrosion. But if you see, this is no other deposits such as iron sulfide or iron disulfide is included in our test. So these two remain still a challenge. Hence, we said, okay, let's come up with a few objectives. The first one was to develop a rapid electrochemical testing technique for corrosion inhibitor qualification. And we also wanted that to include the effect of deposits such as iron sulfide, iron disulfide, and silicon dioxide. So then we decided to go with the electrochemical testing cell that you can see here, because electrochemistry, for obvious reasons, can help us in, carrying out or testing various conditions, and also the duration of the test is pretty fast. So if you look at, for example, I will tell you a little bit on how we managed to build these deposits and how we managed to test this here. We decided to do electrochemical impedance spectroscopy. So this was done at Qatar University and Imperial College London with the teams there. So we had, this was a simple setup. We did a quick test. I don't want to get into details because I just, I also realized we do not have a lot of time. So if you see, the EIS measurement that was carried out in the presence of deposit. So we tried to do some partially covered deposit, compare that with fully covered deposit. And also we got some deposits from the field. We had this tested in the various inhibitors. We did some EIS spectroscopy on them as well. In the end, if you see, we were able to qualify inhibitors in about 20 minutes of tests, So inhibitor per condition taking 20 minutes versus 500 hours, you can see it makes a world of difference. Also, we were able to compare the performance of one inhibitor with the other and also come up with the optimum dosage. So far, all the tests that we do only talks about minimum dosage of inhibitor that is required. One of the things that this study really brought out is that you can see as the inhibitor's performance reaches the peak, beyond that, when you increase the concentration of inhibitor, actually the corrosion rate also tends to increase. So this was a eye-opening study for us, and we said, okay, overdosing of inhibitor in the pipeline is going to cause significant challenge. Hence, the optimum dosage has to be targeted, and this cannot be done without having an electrochemical test, because simply we cannot spend years qualifying an inhibitor for various concentration. So that was one of the things that came out of the study, and this has now been implemented in qualification of inhibitor for Pearl. So this has already been deployed in the field. And then I told you about the different kinds of deposit that we were testing, so such as iron sulfide, iron disulfide, and silicon dioxide. So we also tried to build these artificial deposits onto this and to see how the inhibitors performed in the presence of deposits. And we could clearly see that, iron sulfide was something that was extremely corrosive as compared to iron disulfide and silicon dioxide. And this was demonstrated at CR11, just one of the inhibitors that we were testing, turned out to be one of the best inhibitors to prevent any further. I mean, it performed better even in the presence of deposits, and this has also never been done before. So, we felt so happy, as a result of which we managed to develop or design a coupon. So I told you about the coupon that goes into a slug catcher, which we retrieve once every 3 months to do corrosion rate assessments. So now we have patented about the design of a coupon which has this artificial deposits in, and which is now currently being deployed in the Pearl pipeline. So we have completed 6 deployments so far. 6 times we have retrieved the coupon data, and this data as of today is helping us in solving some of the biggest challenges that we have in terms of understanding how each one of these deposits perform, what happens in the presence of sand, for instance, what is the kind of pitting, nature of pitting, depth. And this could have never come out if we did not have this study. So also the effect of coverage. So partially covered versus fully covered was behaving so differently. So as a result, we could also understand what is the extent of coverage of deposits in the pipeline, for instance, if in case we get these corrosion rates. So we're able to compare our field data to the lab data. And this is what we really want to see in our projects, the element that can be taken back to the site, and it helps us in operating our assets better and improves the integrity of our asset. So on the whole, I told you about the challenges that we had about duration of the test conditions. So the 2 projects that were carried out for this was early detection project and inhibitor project. This was with Qatar University and Imperial College London and Indian Institute of Science. And so with this, we have come up with a good innovative electrochemical technique, and which I said has been deployed in the site. And so Qatar University played a very important role in electrochemical tests. The expertise in Dr. Bakker's team, where they brought in the idea of doing EIS spectroscopy on that was amazing. Imperial College London also, on the other hand, has supported us with carrying out advanced mechanistic study and also a lot of synchrotron-based study in the presence of H2S, because you know that H2S testing is not really allowed in Qatar. Indian Institute of Science supported in the model development. So all the data from QU and ICL are put together to develop a model. And Shell, from our end, not only we support these projects by in-cash funding, but also with a lot of in-kind and our own in-house R&D. So Shell Technology Center specializes in a lot of these tests. So we have also been contributing to looking at these studies very closely. So as I said, this technology has been transferred and is being utilized currently for the pipeline. In terms of pitting on the UDC, as I said, we had two projects. So this is UDC in the pipeline and the new sensor project. So far, you would have seen this article that came out in the newspapers and also in the Qatar Foundation news. So we have deployed these modified or smart coupons in the field, which is being used by Pearl right now to understand under deposit corrosion and also how that has an impact in the pipeline. So it's given us a lot of insight. Qatar University and Imperial College have been participating in this work. Again, Qatar University carried out the electrochemical and deposit simulation work. Imperial College was doing the synchrotron study, and Shell from QSRTC's end, we were involved in designing and manufacturing and field testing of these modified or smart coupons. So the outcome is the smart corrosion coupon that we have, 2 patents that have come out of this, and multiple articles, and also in terms of publication in the newspapers and a lot of visibility. So the example that I showed you contributes to 4 projects that you see here, CR1, 20, 9, and 5. So that is just about the pipeline. But our Pearl GTL and any asset has a lot of other units, a lot of other equipment. So that's how all the other projects and all the other 24 projects come into picture, out of which we have 14 ongoing ones. And this is how we operate. So the current challenges, the real challenges in the asset get translated into an R&D project and then goes into field deployment. If we have further questions, then we continue the R&D project, and this is how we make sure we support the mechanical integrity team of Pearl GTL. I would like to acknowledge and thank Dr. Shakur and Dr. Mansoor for the opportunity, and also the organizing committee of Emerging Materials Conference. I think I really enjoyed when I was putting these slides together, and I'm very glad to be here. And I'm very thankful to Dr. Bakar and team and Dr. Mary Ryan and team from Imperial College and Qatar Foundation and QNRF for the funds, especially for the NPRP projects that we have ongoing in the pipeline related work, which was showcased here. That's all from my end, and I'm very glad to have any questions that you might have. Thank you.
Thank you very much, Dr. Bita, for sharing the recent activities at Qatar Shell really very impressive, the research that is being conducted at QSRTC with your collaborator.
Dr. Shakur, I cannot hear you.
Really? So can
Can you hear me?
yes, I can hear you. So Dr. Bita, can you hear me now?
Can anybody else hear Dr. Shakur, or is it just me?
Yes, everyone else I think can share.
So anyway, Dr. Bita, thank you very much for sharing the recent activities at QSRTC. So wonderful research activities being undertaken in your institution. So you have been very kind to us, and thank you very much for providing many research fundings to the academic institutions as well. So keeping in with the time limitations, if we can handle only one question, if anybody has.
There is a question in the chat box.
Dr. Shakur, I still cannot hear you, so I'm not sure why.
No worries, Dr. Bita, still fine, no worries. So then we can move to the next speaker.
Bilal, can you hear
Yes,
Dr.
we
Shakur?
can hear him.
Or is it just me?
No, we can hear him, Dr. Abitha. Dr. Abitha, there is two questions in the chat box for you from Dr. Chowdhury and from Hanan Tariq and from Adnan Khan also.
Dr. Bitha, can you answer those questions? I think my voice is not, clear to Dr. Bitha. So anyway, because she is still with us and she is in Doha, we can ask this question from her directly later after this session. So let's move to our next speaker. Our next speaker is Dr. Vivek. He is a lead product development chemist in USA. Let me introduce him. Dr. Vivek is currently working as a lead product development chemist at PPG USA, focus on industrial coatings. He did his Bachelor's of Chemical Engineering degree specialization in coatings and polymeric materials. He started his career with BASF Coatings, where he was focusing on automotive coatings. After 6 years of working at BASF, he moved to United States for his graduate degree to University of Southern Mississippi, where he earned his PhD in polymer science and engineering. After PhD, he joined Sherwin-Williams as a senior chemist, developing new platforms for test development to predict corrosion. After working there for 3 years, he moved to PPG USA, where he is currently working. Please welcome Dr. Vivek.
Thank you. Thank you for the kind introduction, Dr. Shakur. And it's a great pleasure to meet you all. Can you see my screen?
Yes, we can see. Can you go to the presentation mode?
Yeah, sorry. Let me share. Is it in presentation mode?
Yeah, it is fine now. It is fine now.
Okay. Okay. Thank you. Good evening to all. It's November 23rd morning, 11 o'clock here in the United States. Today I'll be talking to you guys about emerging trends in corrosion detection in industry. And I assume all the participants here are corrosion experts. So let me start with briefing about what we know about corrosion and then jump into the emerging trends. So this will be the roadmap for today's talk. First, we'll be talking about corrosion and its type, and then we'll be discussing about the theory, followed by the importance of corrosion monitoring, and then we'll be discussing about common techniques that are being used in industry for high throughput. At the end, it is worthwhile to discuss some emerging electrochemical methods that are used in laboratory for corrosion studies by researchers. In the first session, we'll be focusing on corrosion. Why do we care? Why do we care about corrosion? Because we live in metal-based civilization, starting from transportation to sustainable resources, to food and oil and gas transportation. So everything is based on metal, and that's why we care about corrosion. To begin with, what is corrosion? It's an electrochemical process of destruction that converts metal to more thermodynamically favorable state. To understand this statement better, we have to understand the corrosion cycle. Every metal is a naturally occurring element in its most stable state that are present on Earth in its oxide form. After mining, the alloys are processed into minerals that we use today in our daily lives, like automotive ships, etc. This form of alloy is most thermodynamically stable state. So when it is exposed to harsh environment, corrosion starts, which go back to its most stable state, that is its oxide, completing its process cycle. The motivation to mitigate corrosion can be divided into cost, safety, and conservation. In terms of cost, currently 3.4% of world's GDP is spent on cost of corrosion. The pie chart shows a breakdown of cost of corrosion at 5 different areas, majorly spent on servicing and maintaining corroded surfaces. In this slide, I'll be talking about the forms of corrosion. Since we all knew about this, I'm gonna quickly show uniform attack, full-size attack, stress corrosion. It can be pitting, filiform, galvanic corrosion, and erosion type corrosion. I'm not gonna go in detail since we all know these types of corrosion for the sake of time. And these forms of corrosion discussed can be dependent on the substrate used and the environment that they are exposed. Since every market segment uses different substrate, as shown in the slide, it's very important to pay attention on all types of corrosion. In the second session, we'll be talking about the corrosion theories. There are several theories of corrosion that have been proposed time to time, but there are three major theories exist. The first is the acid theory, which happens when there are acid in the environment. Second is the chemical corrosion, also called as dry corrosion. The third is called the wet corrosion or electrochemical reaction. We will discuss each of these and its mechanism of corrosion in the following slides. Acid theory of corrosion considers to be the main acid theory of corrosion. Acid is considered to be the main cause. Rusting takes place faster in acid solution than in neutral or basic solution. Oxygen and water are necessary for rusting of iron. The mechanism is shown here in here, where the metal such as iron is exposed to acidic gases such as carbon dioxide. In the presence of oxygen and moisture, it forms iron hydrogen carbonate, which further decomposes to form carbonate form of iron hydroxide. This further, in the presence of moisture, generates iron hydroxide along with liberating CO2 gas, which further catalyzes the reaction. This theory is supported by the presence of CO2 ion in the rust analysis. The chemical or dry corrosion happens because of the direct chemical reaction of environment or atmospheric gases or inorganic liquids with metal surfaces. There are three types of chemical corrosion: oxidation corrosion, corrosion by other gases, and liquid metal corrosion. In the chemical type of corrosion, it is carried out by direct action of oxygen at low or high temperature on metal in the absence of moisture. Most alkali and alkali earth metals rapidly oxidize at low temperature. At high temperatures, all metals except silver, gold, and platinum oxide. turns into an oxide. So in step 1, when temperature increases, the metal undergoes an oxidation and loses an electron from the metal ion. Then in step 2, the electrons are gained by oxygen molecules. Did I miss?
Dr. Vivek, we can hear you.
Oh, I'm sorry. I was I didn't know I missed you guys.
No, it's fine now. It's fine now.
Can hear you
Okay.
very well.
Okay. Can you still see my screen?
Yeah, it's fine. Everything is fine. Just keep on presenting.
Okay. So in dry atmosphere, you guys can hear my echo.
No, Dr. Vivek, we can't see your presentation. We can see many screens on your desktop.
Let
You
me.
might be out of the system, Dr. Vivek. It's okay if you get out of the system. Don't worry. Just sign in again or join the link again, and I will assign you as a speaker.
Okay.
I think the WebEx will kick you out now because of this lag. Okay. Now it's okay.
It's fine now. It's fine now.
No, it's fine. Yeah, you can proceed.
Okay. In dry atmosphere, you still can see my screen, right?
Yes.
No, it's fine. It's fine.
Okay. Thank you. In dry atmosphere, these gases react with metal and form corrosion products, which may be protective or non-protective. For instance, in dry atmosphere, chlorine reacts with silver to form silver chloride, which is protective layer, whereas with tin, it is volatile. Another example in petroleum industry, where H2S gas at high temperature reacts with steel, forming a FES scale, which is highly porous. In terms of liquid metal corrosion, the chemical action of flowing liquid metal at high temperature on solid metal or alloy. The corrosion reaction involves either dissolution of solid metal by liquid metal or internal penetration of liquid metal into solid metal. In the final theory, electrochemical corrosion, the diagram illustrates an electrochemical reaction occurring at the surface of the metal covered with a film of water containing dissolved oxygen. The two reactions involved in the corrosion are shown. Metal atoms dissociate into metal ions and free electrons in oxidation reaction at the anode. These electrons migrate in metal and initiate the reduction reaction at the cathode that generates the hydroxyl ions. Now we will be talking about the core of today's talk, which is corrosion monitoring. That is referred to corrosion measurements performed under different industrial or practical operating conditions. In this session, we'll be focused on types of technique used in monitoring the corrosion in industrial wide. This chart here represents different techniques used. Since there are a number of different types of corrosion, and corrosion may be uniform on a huge area or concentrated over small areas, there is no single measurement technique that will detect all of these various conditions. Some corrosion measurement technique can be used online, constantly exposed to the process stream, while others provide offline measurements such as that determined in laboratory analysis. Some techniques give a different measure of metal loss or corrosion rate, while others are just used to infer that the corrosive environment may exist. Performance evaluation in service materials by corrosion monitoring is highly relevant because laboratory data may not be applicable to the actual operating system. The common monitoring techniques include the use of corrosion coupons, electrical resistance, and linear polarization resistance. The weight loss technique is the best known and simplest of all corrosion monitoring techniques. The method involves exposing a specimen of material, a coupon, to a process environment of a given duration, then removing the specimen for analysis. The basic measurement, which is determined from corrosion coupon, is is weight loss. The weight loss taking over a period of exposure, say 90 days, being exposed as a corrosion rate. This corrosion rate is expressed as shown in this equation, where the corrosion rate is expressed in millimeter per year. Delta W is the weight loss of the specimen in grams. A is the area of specimen in centimeter square. T is the exposure time of the specimen in corrosive environment in hours. Rho is the density of the specimen in grams per centimeter cube. And K is the constant for unit conversion. Advantage of weight loss coupons are that the technique is capable to all environment, including gases, liquids, and solids. That is particulate flow. Visual inspection can be undertaken. Corrosion deposits can be observed and analyzed. Weight loss can be readily determined and corrosion rates easily calculated. Localized corrosion can be identified and measured. Inhibitor performance can be measured and accessed. The main disadvantage include the human error, the error associated with handling the coupons. Since it is periodic measurement, it can be time consuming, and the actual part might have deteriorated before the coupons can indicate. So this technique cannot be used as a predictive method. It's just a monitoring technique. Electrical resistance probes, ER probes, can be thought as electronic corrosion coupons. Like coupons, ER probes provide a basic measurement of metal loss. But unlike coupons, the value of metal loss can be measured at any time. As frequent while the probe is in situ and permanently exposed to the process stream, these measurements can be done. Electrical current is applied to the element or an electrode, and the resulting resistance is measured against a reference electrode. Resistance increases as the element or electrode loses metal through the corrosion process. The ER technique measures the change in ohmic resistance of a corroding metal element exposed to the process stream. The main advantage include direct corrosion rates can be obtained. Probe remains installed in line until operational life has been exhausted. They respond quickly to corrosion upsets and can be used to trigger an alarm. The main disadvantage with these techniques, again, it's a monitoring tool, but not a predictive tool. The next important technique is linear polarization resistance, or LPR. Is based on electrochemical theory. In fundamental, a small voltage, which is called polarization potential, is applied to an electrode in solution. The current needed to maintain a specific voltage shift is directly related to the corrosion on the surface of the electrode in the solution. By measuring the current, corrosion rate can be derived. The ratio of potential change to current density change at corrosion potential region is called polarization resistance, that is inversely proportional to the uniform corrosion rate. And with the help of Stern-Gray equation, as shown here, the polarization resistance can be calculated. The main advantage of LPR technique is that the measurement of corrosion rate is made instantaneously. This is a more powerful tool than either coupon or electrical resistance method, where the fundamental measurement is weight loss, where some period of exposure is required to determine the corrosion rate. The disadvantage of LPR technique is that it can only be successfully performed in relatively clean aqueous electrolyte environment. So in case of turbid or mixed slurries, this cannot be used. And LPR will not work in gases or water oil emulsions, where fouling of electrolytes will prevent the measurements made. In the above said methods, the probes were in contact.
Dr. Vivek, sorry for interruption. Can you conclude, because we are running short of time, please?
Okay, yeah. I just have this table just to give the audience general ideas about waveguide and infrared thermography and microwave, and it has its own advantage and disadvantages. While this technique can be used online, there are other techniques, electrochemical methods such as scanning vibrating electrode technique, electrochemical microscopic scanning Kelvin probe, and droplet cell technique, which is also used in laboratory scale, and it has its own advantage and disadvantage. And with this, we will have with this. I would like to thank Dr. Internet. So I may take any questions you may have.
Thank you. Thank you very much, Dr. Vivek. We can take one question from the audience. Is there any question? If not, once again, thank you very much, Dr. Vivek, for sharing very nice presentation with us and joining us for today's session. Thank you very much.
Thank you so much.
Then we can move to our last speaker, Engineer Mohsen Al-Haddad, who is Senior Well Integrity Engineer, Qatar Gas Operating Company Limited. Let me introduce Engineer Mohsen Al-Haddad. Engineer Mohsen Al-Haddad is a Senior Corrosion and Well Integrity Engineer with more than 19 years of experience in oil and gas industries. Mohsen has wide experience in the fields of our material selection, chemical treatment, coating management for upstream and downstream processes. Engineer Mohsen has participated in several research projects as principal investigator and published several high-performing technical papers. Engineer Mohsen holds master degree in material science and engineering, and fortunately, he has been our student. So I welcome Engineer Mohsen to share his presentation today.
Thank you very much, Dr. Abdi Shakur. I'm just trying to share, but it gives me that I think my for one reason.
Brother Mohsen, just you open your presentation and then share screen. It will automatically appear on the system.
Just let me. They said you have to quit now. Oh.
Ms. Noorbadar, can you guide Engineer Mohsen?
What's your problem, Engineer Mohsen?
They gave me, I have to give preferences when I share, go to system preferences, open system preferences to allow for sharing. I do not know why it's not sharing.
Just 1 minute. Can you try now? Can you try now? You can press Control Shift D, and check what appears to you. And the same time, Control Shift D.
This is MacBook, this is very.
Okay.
This is the issue. Let me check just a couple of minutes. I'll have my.
Okay, no worries. You are the last speaker. No worries. We have time.
Yeah, but we don't want to stay up to midnight.
That is why I put you in the end.
That's what. trying to.
Engineer Mohsen, do you want me to share my screen with you to show you how to share?
Yeah, please. I know how, I just clicked the share, but it gives me, you need to grant access in system preferences.
Okay.
I'm not sure.
For privacy, maybe because you are from the MacBook.
Sorry?
Maybe for privacy because of MacBook, because you are using Apple.
Yeah, maybe this is the challenge. Yeah, I'm trying to go to privacy, firewall.
Mohsin, you can send the presentation to Dr. Shakur and he can display it for you and you can narrate.
Okay, maybe this is an option. Yeah. We send it to Dr. Abdul Shakur.
You are sending it to me?
Yeah, I'll send it now. MB. Okay, I can use my other laptop, so it's 1 minute.
Okay.
Sorry for that, guys.
I haven't received, Brother Mohsen, your presentation.
No, I will. It's 13 MB. It's very difficult. So I'm opening my other laptop, company
Okay,
laptop.
okay.
So this will be very easy.
Okay,
I have
okay.
other options. So I know this technology sometimes make you fail down.
Okay, no worries. We will not miss you at any cost. We are quite eager to listen to you.
Thank you very much. I'll open now the
Rasmussen, are you with us?
Yes, yes, I am opening now. Yes.
Okay,
just
okay,
opening the
please,
laptop.
please.
Sorry, guys. Sorry for this.
No worries, take your time, no worries.
I'll quit and join again. Okay.
Okay, okay, no worries.
Okay. Thank you. Okay, now it's working.
Okay.
Sorry, guys.
No worries, no worries. No.
I had to take a board of my IT and small engineer.
So now we can see your screen, but yes, no, it is right.
Okay.
Yes.
Now I'll open the camera. Just 1 second. Sorry. You cannot see me, can you?
No worries. We can. No, your presentation is away.
Yeah, very good. This is very good.
Previously, it was fine.
Yeah. I know this. How to can enable the video? Oh.
No worries, no worries. Video, only we need your presentation.
Okay. Thank you very much. So I'll share the presentation now.
Yeah, just share presentation. Yes, okay.
Okay.
Yes, okay.
Thank you very much for having me. Can you hear me now?
Yes, we can hear you well.
Okay. Thank you very much for having me. This is a topic for thanks again for accepting my invitation or my presentation to be included in this conference. The presentation will talk about corrosion inhibition experiment of mild steel at elevated temperatures in highly acidic primes using a green corrosion inhibitor. This is a legal disclaimer from the company that the company does not bear any responsibilities, neither liabilities for any accuracy of the content. We will talk about the introduction, about the topic. Then we'll have to review the objectives, experimental work, results discussion, and then conclusion, and finally acknowledgement of the supporting team. As you know, safe operation of refining and petrochemical plant is considered one of the most critical and challenging tasks. And processing, treatment, storage, and transportation of highly corrosive and hazardous fluids are required on a day-to-day activity. Therefore, managing asset integrity is vital for oil and gas companies because it's part and parcel of managing the risk portfolio and overall. So therefore, the process of extracting oil and gas is getting more challenging, whereby the search for new sources has expanded to complex geographical locations. Unfortunately, tragic incidents frequently occur due to loss of mechanical integrity. As you know, after PP Macando incidents, many oil and companies were forced to relook and reevaluate their facilities' asset integrity to minimize their risk exposure. Therefore, asset integrity must be maintained at the highest possible standard at all times. Due to the unique nature of subsea and its remoteness, asset integrity shall be paid high attention from beginning of a project's life cycle. Little bit on the corrosion trends. This is a corrosion trends produced by API, reveals that corrosion is the second contributor to facility releases and loss of primary containment. This stimulates researchers, that's why we are all here, to exert more efforts in order to mitigate corrosion threats. Similarly, U.S. Federal Highway Administration released a breakthrough 2-year study in 2002 on the direct corrosion costs associated with metallic corrosion nearly every U.S. industry sector, from the infrastructure and transportation. This was initiated by NACE International and mandated by the U.S. Congress in 1999. The study reveals, as you can see, the cost estimate for the time and identifies national strategies to minimize the impact of the corrosion. And according to this study, the direct cost of metallic corrosion is evaluated to be 270 billion on annual basis. In GCC countries, a recent study also indicates that alarming corrosion costs in just 5 years, for example, the corrosion cost in Qatar had almost doubled from $4 billion to $8 billion. This is only the direct corrosion cost, excluding, of course, the operations, upsets, and loss of production. This is the objective of the study. Acidic corrosion, as you know, and oil and gas operators have used acid treatment, acidizing, and to improve volume protectivity for almost 120 years. However, the acidizing use was limited by the lack of an effective acidic corrosion inhibitor to protect downhole tubulars and completion in wells and upstream equipment, because the post simulation will flow back to the asset, and we need to ensure that the backflow or the depleted stimulation fluid does not pose any corrosion threat to the asset facility. There are 3 general categories of acid treatment: acid washed, matrix acidizing, and fracture acidizing. The treatment selection, of course, process dominated by formation type and dominated also by the corrosion inhibitor to be used. Hydrochloric acid is famous for being utilized in stimulation treatment programs. It reacts with the carbonate to form salt and carbon dioxide and water. When acidizing sandstone with hydrochloric acid reaction are more complex. Of course, that's why they tend to use hydrochloric acid, which is more versatile. Acidic corrosion also, they use in the acidizing high concentrated HCl. And as you know, the downhole temperature can reach more than 100. So corrosion, of course, adds operating cost, and that's why we need to mitigate this risk. HCl also is used in cleaning and acid pickling treatments in the acid and heat exchangers. What is the corrosion control methodology simplified? And this is the kind of corrosion control simplified that if we control the corrodant, we will be able to control corrosion, and that's why we are trying to influence the environment to mitigate the risk of corrosion by making the environment less corrosive and also applying a barrier layer over the downhole tubulars. The objective of this work is to successful introduction of a reliable green corrosion inhibitor. Why do we need a green corrosion inhibitor? Because disposal of uninhibited or inhibited water to the sea or to the closed drain is very challenging and adding a cost because of the environmental regulation. So if we successfully introduce a green corrosion inhibitor that can suppress the corrosion rate and it's environmentally friendly, this will be, of course, a success to all. What did we select for this experimental work? This is a typical composition of a downhole L80 type 1 material. The specimens were of course, grinded using silicon carbides, and then acid solution was prepared by diluting concentrating hydrochloric acid in a distilled water to produce 16% solution. And this is the chemical formula for the loradamide proamine oxide. This is the first time used. This is a surfactant that it's also used in some of the children and human disposal material. So it's not really corrosive or has any environmental impact. We have utilized the electrochemical measurement in a double jacketed Pyrex glass and using Camry 300 and potentiostat galvanostat with a thermostat to ensure that the temperature stays constant. These are also some of the equipment that are used for the characterization of the specimen. Potentiodynamic polarization studies were done at different temperature, 20, 40, 60, and 80, and at different concentration of the corrosion inhibitor. You can see that this was also used to calculate the corrosion current and also the inhibition efficiency and polarization resistance, which I'm going to show you in the coming slides. These are the parameters we were collected from the potentiodynamic polarization curves. As you can see, the corrosion current was significantly reduced at 20 degrees to 0.08 milliamp per centimeter square, which is corresponding to a higher inhibition efficiency of 94. This is the highest. And when you go down at 80 degrees, for example, the inhibition efficiency will slightly decrease because of, because of the dissolution of the corrosion inhibitor and the thermodynamic influence of the temperature on the corrosion rate. Also, electrochemical impedance spectroscopy, as you know, is a powerful technique that's used to study electrode-electrolyte interface. This technique has been used to understand different corrosion reactions and estimate their rates. Different curves for mild steel and 5 molar HCl in absence of corrosion inhibitor at different temperature were established and analyzed using the electrochemical equivalent circuit. Corrosion inhibition was found to increase in direct relation to the value of the charge transfer resistance. And these are the similar figures were done also to represent the Nyquist plots of mild steel exposed to 5 molar HCl in the presence of different concentration of corrosion inhibitor. As you can see that the resistance increased by increasing the corrosion inhibitor concentration. To review a summary of the parameters, when examined that, you see that the charge transfer resistance increases with respect to the increase in the concentration of corrosion inhibitor as compared to the baseline value in absence of the inhibitor. This increase in resistance is attributed to the absorption of a barrier film of the metallic substrate. On the contrary, to the charge transfer resistance increase, the interface double layer, as you can see, capacitance gradually decreases on increasing the concentration of the corrosion inhibitor oxide. The decrease in interface capacitance is primarily caused by either reduced value of the dielectric parameter or thickness increase of the double layer, as you know, as you know. Also, absorption isotherms and thermodynamic calculations were performed. The applied corrosion inhibitor, the effectiveness and characteristics of the corrosion inhibitor absorption to surfaces, of course, is a key step in the overall inhibition process. The K constant, absorption equivalent constant, also was calculated and plotted the ln K absorption versus the reverse of the temperature as shown in figure B. A straight line was obtained that follows the Van 't Hoff equation. This table also summarizes the value of delta H absorption and delta S and the constant of absorption and delta G for the corrosion inhibitor. The positive values of course, the delta S means that the absorption process is accompanied by an increase in entropy as a result of the exothermic absorption process, which can be seen from the negative value of delta H as well. Another study was done is the effect of the inhibition mechanism and efficiency by studying the activation energy. Of course, inhibition mechanism and efficiencies are directly influenced by the apparent activation energy, and a Venus plot of the mild steel logarithmic current density log I versus I versus the reverse of the temperature and absence and in presence of the corrosion inhibitor are given in figure A, with a linear regression rate that is close to unity. As in figure B, if you can see, straight lines were obtained by plotting log I over T versus the reverse of the temperature at different concentration of the corrosion inhibitor. The enthalpy of activation and entropy of activation for the corrosion of mild steel and 5 molar HCl were also calculated from the transition state equation described by some of the authors. And this is also the effect of activation energy summarizes in the temperature corrosion rate. Surface analysis was performed using scanning electron microscope imaging for the sample before immersion and after immersion. You can see in figure A, shows a smooth surface with no visible signs of corrosion and then 5000x magnification. A significant corrosion suppression was noted with a relatively smooth surface, which, for example, in C, suggesting that a formation of a very effective barrier because of corrosion inhibitor. AFM also was also performed. As you can see, that images for the mild steel without air. After immersion of 24 hours absence of corrosion inhibitor shown in P, showing a very high deep bits. That's when the corrosion inhibitor was introduced in C, it was showing a significant reduction in the corrosion rate. What is the status of the corrosion inhibitor? Is it absorbed to the surface or not? That's why we did XPS. To investigate the composition of the organic absorbed layer on the mild steel surface in hydrochloric acid, and you can see also that there are some oxygen O1 visible in the X-big spectrum, which indicates that the corrosion inhibitor is still absorbed to the surface.
Brother Mohsen, can you conclude? We are running short of time, please.
Yes, so this is the conclusion now. Sorry for that. I'm just rushing through the slides. So conclusion, excellent inhibition properties for the corrosion and corrosion of mild steel in 5 molar HCl. The inhibition efficiency increases with increase of inhibitor concentration. More than 94% of inhibition efficiency was successfully achieved upon addition of 370 micromolar per liter of the corrosion inhibitor from a tested corrosion inhibitor. And the absorption follows Langmuir isotherm. Inhibitor suppresses the oxidation and reduction reactions. Therefore, it's classified as a mixed type corrosion inhibitor, follows a chemi physioabsorption nature. And XPS, as I said, results corroborate thermodynamic results and give evidence of the chemi physioabsorption of the corrosion inhibitor at the surface. And also electric impedance spectroscopy methods are in good agreement. Future work for this is to perform a dynamic assessment of the inhibition efficiency and also expose it to different types of material like nickel alloy, because you know that downhole completion we have different types of material. This work was published in as a scientific open report for anybody who's interested to go in more detail to this report. And I really like to acknowledge the Material Science and Technology Master Program for their support, the Thesis Supervisory Committee, Center of Advanced Material, and finally, Emerging and Enabling Material Conference Organizing Committee for accepting this presentation to be presented. And thank you very much for listening.
Thank you very much, Engineer Mohsen, for your great presentation. So, any question, if anybody has?
I don't think anybody has a question because they are rushing to have some sleep.
No, it's a great presentation and great knowledge sharing. So before conclusion of the session, I would like to thank all our distinguished speakers and all the audience who have made this event successful. And I need to acknowledge the great support of Texas University at Qatar, and especially the Dr. Bilal Mansoor, who did a great sport to make this event a successful event. Moreover, I would like to acknowledge the Qatar University team, Noor Badr, Dr. Khatija, Dr. Sajna, and our IT experts. So because of your great support and the cooperation, we have successfully concluded this wonderful session. I hope the audience have enjoyed this session. Before conclusion, I would request Dr. Bilal Mansoor to say a few words. Dr. Bilal Mansoor.
Well, thank you, Dr. Shakur. Again, I'd like to thank everyone that was involved, especially the technical team. But thank you to you as well. You did an amazing job in putting all the presenters together. It's always difficult to engage folks, especially later in the day, as Mohsen has also mentioned, right? So thank you to all the speakers for taking the time, and especially the attendees. I think this went very well given the timing, and we're all getting bored from being online. So let's hope that next year we do this in person, and that will also be one step back towards normal how the material symposium used to be. So great job, and thank you so much, everyone. Good night.
Thank you very much, Dr. Bilal Mansoor. So we officially conclude this session, and thank you once again for everybody for sharing with us and staying with us. Have a good night. Allah Hafiz.
Thank you guys. Thank you very much. Really appreciate it.